So we have a program with long talks for the morning on the first afternoon session, and then the second afternoon session, there is a bunch of small, fast talks. So, and afterwards, so we plan to go to a pub, which is called Your Old Cheshire Cheese Pub. Okay, so maybe during the break I will put the name and the address. It's a 15-minute walk. Okay, so please, starting at 6, you can join us to this pub. But we don't have much sponsoring, so it's you will have to buy your drink. But we have planned some cheese for you, because the tradition is cheese and wine, but it could be cheese and beer because we are. So please welcome the first speaker this morning, Xavier Leroy, who does not need any introduction.
Thank you, Antoine. So good morning, everyone. Can you hear me? Okay. Can you project my slides, please? Yeah, so when the, and thanks the organizer for inviting me, although, yeah, when they invited me, I didn't quite I misread the title of the workshop, okay? I just read 40 years of abstract interpretation. I forgot the next part. And so I thought it would be like, you know, celebrating 40 years of great achievements, and as a great admirer of the work that's been done in this community, I could just say a few words and then some anecdotes, and nobody would notice that I'm definitely not an expert in abstract interpretation. And then I got another mail from Antoine saying, okay, so this is the next 40 years of abstract interpretation, and you have 45 minutes and you go first. All right? So I will do my best. Thank you. And I will start with an anecdote. So actually, like many people in this room, I discovered abstract interpretation by taking the course taught by Patrick and Radia. I think it was in '89. And that was perhaps one of the first times they were offering it at ENS. I was an ENS student. And so all ENS students were in CS were encouraged to attend. They told us, no, it's a very new course and there's no prerequisites. I had basically zero knowledge of programming language semantics at that time. And so I went, and it was tough. Yes, there was no prerequisites, but you had to absorb Hoare logic and Scott domains in 30 minutes each. And it went very fast, as you all know. And it was at an ungodly hour, like 8 a.m. on a Monday morning. So my main recollection is fighting, you know, sleep and trying to stay awake and just absorb everything that was being flashed on the screen. Okay, and so afterwards I did a PhD in type systems. At least that was a little more accessible to me. And then, much later, I ended up doing static analysis, not very complicated ones, you know, data flow analysis in the OCaml native code compiler. Later, when I worked on Java bytecode verification, and well, more recently, when I did the CompCert verified compiler, there's a bit of data flow analysis to support a few optimizations. And so, like every 5 years, I would have an epiphany, you know, saying, "Oh, that's what Patrick and Radia meant." Oh my God, that's brilliant. So yeah, and it's also when working on static analysis that I discovered mechanized proofs. I started to do cog proofs basically at the same time I was doing Java bytecode verification. I had a verification algorithm I really wanted to trust. So that was tough, but that's how I discovered mechanized proof. And so I thought I would kind of combine both, and that's one of the projects I will describe briefly, and basically talk to you about both, so abstract interpretation and its mechanization. All right, so why mechanize abstract interpretation? There are two completely different reasons, orthogonal reasons. One is that static analyzers deserve formal verification. They participate in the construction of critical software, right? And so, like all other tools that participate in the production of critical software, you know, this is my background screen, but okay, let me see if I can do something about that. I used to be in mirroring mode, but maybe I went out of it without noticing. View, presentation, okay, crossing fingers. Okay, not crossing fingers. Now it's mirroring again. Okay. Okay, wait a minute. Maybe I will unmirror and it will work better. Who knows? Shit. Where are the displays? Here. This is a great system, but you should ask people to... Oh, now it's unmirrored. It's unmirrored, but it's not showing anything. So, wait a minute, I have an idea. Okay, it's mirrored again, cross fingers. All right, so yeah, I was saying static analyzers participate in the verification of critical software, and I think every tool that participates in the verification of critical software deserves some formal verification to build trust in them. And of course, abstract interpretation is a framework that guides the construction of static analyzers and their verification. Okay, just listen to me, okay? So that's motivation number one. And then there's motivation number two, which is that abstract interpretation is a beautiful theory. And it's a general trend these days towards mechanizing nice mathematics, okay? Just to, well, because it's a pleasure, because we may learn some new things or new way to present them. So maybe we will learn new things about AI. Go ahead. And it's also kind of a stress test for many proof assistants, as we will see. So, okay. Crossing fingers. So another first to say that it would be interesting. And so here are some previous attempts that I will mention. Okay. Yeah, we can try another adapter.
Does someone else have an adapter? No, I don't think so.
I've had some problems with this one actually, but not that one. So let's see.
Yeah, we just got like the same one.
Okay. Now it's not mirroring. Well. All right. So, oh, yeah, now I'm not going to see my slides. Well, never mind. Pretty good, thank you. That's fine. Okay, so there have been several projects using COG or AGDA for the proof assistance, as far as I know. And the earlier one, as far as I know, was the master's internship of David Monio, who's somewhere in the room. And so that was back in 1998. And well, that was pretty brave. I mean, he set out to formalize, mechanize abstract domains and Galois connections, all into plenty of problems, and we'll see why pretty soon. Plus, at that time, the COG system was extremely primitive and hard to use. So you can read David's irritation between the lines of his report. That's funny, but that's an interesting document. Then came the PhD thesis of David Pichardy, so 2002, 2005, advised by David Cacherat and Thomas Jensen. So learning from the difficulties that David Monio had, he didn't set out to formalize the whole theory of abstract domain and Galois connections, but just some kind of gamma-only domains and proving only soundness, but also proving termination of analysis, fixed point iteration. And the one application was an interval analysis for the Java card bytecode. And then about 10 years later, we, with David and I and several others, we did the Verasco project, which was even less ambitious in terms of theory. It was gamma-only soundness, and we didn't even prove termination, but we wanted, we were pretty ambitious. We wanted to do something that looks like Astray with relational domains, etc. And I find it funny to see how theoretical ambition goes down as a function of time, while practical ambition goes up. And the workforce goes up immensely, you know, from a master's internship to a PhD thesis to a funded project with 3 PhDs and 5 labs. And then the more recent work, which go back to the PhD thesis format, is the one of David Daré, advised by David Van Horn, which presents a kind of a new kind of Galois connection, or a special kind of Galois connection that they call constructive Galois connections with application to gradual typing. And I'll try to discuss a little bit David Daré's approach at the end. But let me start with a quick recap on Project Verasco. So it's the verification of a static analyzer for C that is based on abstract interpretation, that is written and proved correct in Calc, and that kind of connects to the Concert compiler. So that involves 3 PhD students, Jacques-Henri Jourdan, Vincent Limporte, Alexandre or Alexis Fouillet, and then a number of scientists, several of whom are in the room. And the PI was David Pichardy for the static analysis part. So as I said, the goal was to develop and verify in Calc a realistic static analyzer by abstract interpretation. So we wanted to analyze a Concert subset of C, which is a pretty large subset. We wanted to have non-trivial abstract domains, including relational domains. We admired, we still admire the modular architecture of Astray, so we tried to reproduce that. And we wanted to have Calc proofs of soundness against the Concert operational semantics. And if you need a slogan, so Concert, for me, it was like 1/10 of GCC in terms of quality of code, number of optimizations, etc., number of features implemented, but formally verified. And maybe one of the goals of Verasco was 1/10 of Astray, but formally verified. Okay. I'm not sure we reached the 1/10 bar, but we'll see. So basically, that's the architecture and the main components. So at the top, you have the Concert compiler that kind of pre-processes your source into an intermediate language called C# minor, and that's where we chose to plug the abstract interpreter, which basically analyzes all paths of control, of course, and reports alarms, okay, and is parameterized by a state abstraction, which abstracts over memory states and over pointers, and is parameterized over a numerical domain, which is a combination, a channel-based combination of a bunch of domains. So there are non-relational domains like integer intervals, floating point intervals, integer congruencies, wrapped into a relational interface systematically. So these are functors. Typically, those boxes are functors in terms of ML and Calc modules. And then we also have some relational domains, like the domain of octagons, implemented by Jacques-Henri Jourdan and proved correct from scratch and without matrices, which is quite an achievement. There's the domain of symbolic equalities, and then there's the domain of convex polyhedra, so a linear inequation that was developed at Verimag, and it's the only one that uses validation a posteriori. So there's an oracle that does a lot of operations and produces FARCA certificates, and those are checked by a verified checker. Okay, and I think I mentioned all the boxes. Oh yeah, and this one. So here we use mathematical integers, and at the very end we do modulo 2 to the 32 or 2 to the 64 integers. It's easier this way. Okay. So I'm not going to go over all of this, just give you a glimpse of some of the interfaces used. So what's a generic interface for a numerical domain? For a non-relational domain, there's what is a generic mechanized interface for a numerical domain. So there's a presentation that is pretty popular these days. So it's the gamma presentation used by Pichardy, but also used by Berthaud in course notes, by Nipkoff and Klein in their textbook. So basically, you have a semi-lattice of abstract values, a concretization relation, gamma, from abstract values to sets of numbers, some forward abstract operators with a soundness property, and backward abstract operators to refine conditionals. Okay, so this is pretty standard and pretty easy to formalize in Coq. But when we started Verasco, it was not completely clear what the generic interface for a relational domain was. And we settled on this approach. So there are three major operations: assign, forget, and assume, that change the abstract value. Assign reflects the effect of setting a variable to some simple expression built over variables and constants. Forget is for just non-deterministic assignment to a variable, and assume whether a Boolean expression is true or false. And we found that out later that, well, to report alarms and also to communicate with other domains, it's good to have queries like is x less than y, or x mod 4 is 0, and that can be actually expressed as getting a variation interval for an expression, okay, as tight as possible. If it's only one element, for instance, we have an answer to x mod 4 equals 0. And there's also another query, which is whether the expression is always well-defined or can go wrong. Okay, and that gives this piece of Coq code, this Coq declaration. So it's a class which is basically a record type on steroids, but it's a dependent record type, so it contains a bunch of operations on the abstract values, type T, like the top, the join, widening operator, and those forget, assign, assume operations, and non-block and get interval queries. And then the second half is the specification. Okay, so you can also put properties in those records, theorems, and the specifications are phrased in terms of gamma, as I said. So function from T to sets of environments, okay, variables to numerical values. And here's the specification. So LEB is sound, the top is the greatest element, join is sound, forget is, etc. So I will not read all of that. Just point out that it's pretty readable, okay, with a little bit of Unicode notations, and not very long. Okay. A few words about the abstract interpreter for the C# minor language. So it's a little bit complicated because C# minor is like C. It has a complicated control flow. So a statement can exit normally or early by an exit, which is a generalization of break and continue, or early by a return, or early by a goto. We handle gotos. And it can be entered normally or entered by a goto, searching from a label. So that's a complicated flow of control, and each of these flows corresponds to some bits of abstract state. Okay, so this is the abstract state when we enter normally. Here we have a mapping from labels to abstract states, and the interpreter either returns an alarm or abstract states for all the possible outputs. So it's structural abstract interpretation defined by recursion over the statement. We use a local fixed point iteration for every loop, a global iteration for gotos, and we expand all functions at point of call. So pretty simple. And the proof, actually we took inspiration from Yves Berthaud's course notes. So it's possible to prove the soundness of this interpreter straight from the semantics, operational semantics, but it's a bit of a pain to keep track of all those abstract states and control flows. So we did that in two steps using a Hoare logic as an intermediary. Okay, so basically we have a little Hoare logic for C# minor, which has 1, 2, 3, 4, 5, 6. It's a 7 tuple Hoare logic because there's 2 preconditions and 4 postconditions. And it's easily proved correct with respect to the small step operational semantics of C# minor. And then we prove that basically the abstract interpreter produces, if it doesn't report an alarm, it produces a valid weak 7 tuple, okay, where you just interpret, you use gammas to go from abstract state to preconditions and postconditions. So it's kind of trivial, but it really simplifies things. And then it let us do more clever things in the interpreter, like unrolling loops sometimes. Okay, and so in practice, so Verasco works. So the soundness was fully proved, 30,000 lines of Coq. We get an executable analyzer by Coq's extraction from production of vocaml code from Coq code. It is able to show the absence of runtime errors in small but non-trivial C programs, but it also needs a lot of improvement. As I said, well, some loops actually need manual unrolling, or only annotations. Otherwise, we are not able to show, for instance, that an array is fully initialized at the end of a loop. And that probably comes from our memory abstraction, which is neither precise nor efficient. and as a consequence, the analysis is pretty slow, up to 1 minute for 100 lines of code. So this is not going to put Astrea out of business. But I think it was encouraging, okay? And then the project kind of stopped because I guess there's not that much interest in informally verified static analyzers after all. But still, so it is publicly available, and I think for some of the techniques that we have, we and MOPSA are perhaps the only two open source implementations available. So, pardon me? I don't know, do they do the channel-based communication, for instance, or some of those very Astrea-like things we try to imitate? I'm not sure. So anyway, so I think Verascore also has a bit of a value as a kind of documentation, let's say, or simple implementation of some of those ideas.
How can it be 30,000 lines?
You mean?
That's a big number.
Oh, no, that's pretty small. Well, I cannot give you a breakdown between specification, code, and proofs. I think some algorithms here are pretty subtle. Just a good integer interval analysis is already a lot of code because there's plenty of cases to consider. Okay.
All of these are covered by the 30.
Oh, yes, absolutely. Oh, no, it's not just, the abstract interpreter itself is maybe, I don't know, 500 lines of code and 1,000 lines of proof. That's pretty easy. No, I think the difficulty is really in all those numerical stuff. Okay.
Why was so slow? Can you comment?
No, actually, I don't know. Well, I don't know. Again, I think the memory abstraction was pretty inefficient, but I can't really give you the details. And as you know, when you get less precise, you also increase analysis times. Okay, you start iterating over huge sets. So that's probably what hit us. Okay. All right. So, but yeah, coming back to what we achieved. So we proved soundness, but we proved nothing else. And that's a little bit disappointing compared with some of the holy texts that I deeply respect, like Patrick's notes at Mark Tuberdov, the calculational design of a generic abstract interpreter. So we have no Galois connections. We have gamma-only domains, but no alphas, which means no optimality guarantees. We don't try to prove that least upper bounds are least upper bounds, just that they are upper bounds. We all our abstract operators can over-approximate, okay? And that's what let us do translation validation for some of them, okay, verification a posteriori. They produce certificates of soundness, but not of optimality. There's no guarantees on the termination of fixed point iteration, so we use fuel. We jump to top after a huge number of iterations, which means that in practice we diverge. There's no proper collecting semantics of the kind that Patrick would find acceptable. And there's no calculations. Everything was kind of implemented, coded, saying, okay, it looks good, and now let's prove it sound. It was absolutely not derived systematically, and I will come back to that later. So all that was a good match for Coq's constructive logic, but well, we were punished by many tops during the development. I mean, it's very easy to miss a case and return top where actually you could have returned something better. And that's awfully hard to debug, as people who write abstract static analyzers probably know. And it was also slightly disappointing. I think in particular, David Pichardy would have loved to stay a little closer to the orthodox presentation of abstract interpretation. So, so let's see what we can do, or what has been achieved. Now, can we mechanize abstract interpretation by the book? Okay, so Galois connections and the calculational style. So, well, as you know, this is a classic Galois connection. So here I'm using sets of concrete values as one of the domains, and then abstract things like intervals as the abstract domains. And so there's this beautiful adjunction property that connects the abstraction function alpha and the concretization function gamma. And one of the good things you can do with that is to calculate sound and optimal abstract operations. You can even calculate program logics, like we saw yesterday, but let me just stick with abstract operations. So if you have an operator from concrete values to concrete values f, then you just write this equation, extend it to sets, compose it with alpha and gamma, and that gives you an abstract operator, f sharp, that goes from abstract values to abstract values. That is sound. So if C is in the concretization of A, then f of C in the concretization of f sharp of A, and that is optimal. So f sharp of A is the smallest approximate abstract value that has that property, and can be calculated systematically. So my calculations don't look as good as Patrick's, but so let's say what's the abstract successor operation in the domain of parity, where you start to write it's the alpha of the set x plus 1, where x is in the concretization of A. And then you unroll some definitions and invoke some general properties of Galois connections, and maybe at some point you do a case distinction, and then you do more good reasons, and you get your abstract operator appears as here a 4-case function, just like Venus rising out of the sea, and it's just beautiful. It's beautiful, it's sound, and it's optimal. Hey. What's the problem when trying to mechanize that? Well, the problem with alphas. First, they are sometimes not well defined. Like if you have rational intervals, this set has no alpha. There's no tightest interval that approximate the interval minus square root of 2. That was a big disappointment when I realized that. Probably I was sleeping when they mentioned it in the lecture. And so I realized like 12 or 15 years later that alpha doesn't always exist. And it felt like, the Santa Claus doesn't always exist. It was, I was really heartbroken. So, but let's say alpha is well defined mathematically. It is generally not computable. As you know, as soon as your concrete domain is infinite, you end up enumerating infinite sets, and it's game over. For instance, for intervals, the alpha of a set of integers or numbers is the infimum and the supremum of the set. And if the set is infinite, of course, infimum and supremum are not computable. Just being able to compute whether a set of intervals has an upper bound or not would solve the halting problem and pretty much all problems in computability theory. So, of course, a computable alpha can only look at a finite number of elements of the set S. Okay. Okay, and why is that a problem? It's that because most proof assistants, or at least those that I know, are logics of computable functions, as Milner's put it, LCF. They vary a lot in their support for classical logic, like Agda is purely constructive, Hall 4, Isabelle Hall are fully classical, Koch and Lean are kind of in between constructive, but it's okay to add classical axioms like excluded middle. But they are all pretty strict when it comes to functions. And having computable functions is great. That supports computation within the prover, extraction to efficient functional code. And of course, you can always add axioms to define non-computable functions. The axioms of description, which are like similar to the axiom of choice, which also gives you the existence of a magic function f. Okay, but again, this tends to break executability in the prover and the ability to extract code. So it's frowned upon. And as we'll see, it doesn't really help actually for the alpha. Okay, so there was a plan B, which is Pichardy's approach, which is no calculation and gamma only, but you can do optimality proofs using gammas only. Okay, so you lose calculations. You need to define your abstract operators F sharp a priori, or calculate them on paper, and then transcribe them in the proof assistant. You need to prove soundness. But optionally, you can prove optimality just with gammas. Okay, it's just a little bit of a pain, and it works. But some elegance is lost compared with the calculational approach. Now there's a plan M. M is like monads, and that's the Daré and Van Horn constructive Galois connections I wanted to talk you about. And it starts with an observation. I don't know if everyone is familiar with monads. So basically, monads, it's a trick to have to add input-output and other effectful computations to a pure functional language, like Haskell, or just the pure lambda calculus, right? And the idea is that you will have a type, M of A, which is a type of effectful computations that end up producing a value of type A. And for instance, print in the IO monad would be a string to M unit. So it takes a string, it prints it, and it returns the trivial value unit. And then you can combine those monadic computations using ret, which injects a value as a trivial computation, and bind that sequences two monadic computations. And the important thing is that there's no projection. From a monadic value in general, M of A, monadic computation, there's no way to just extract the value and treat that as a pure computation, basically. And the observation of Dare and Van Horn in 2016, and they were working in AGDA at the time, is that we could use a monad to separate computable functions, such as F sharp, which, okay, the abstract operator in the end must be computable, and that can only use constructive logic, and separate that from non-computable functions, such as alpha, which will live in a world they call the specification monad, where you can also use classical logic if you want. And the separation would guarantee that in the end, your F sharp you compute would be free of specification effects. And for that, you just write as this. So ret of sub sharp of alpha of A. So this must be a pure value, right? So and ret turns it into a monadic computation. And to the left, you have the equation involving alpha, which is in the monadic world. And then you calculate, and you can even use monad laws if you want, in addition to everything else. And if you manage to put that in a form ret of a pure expression, then you win. Okay, then sub sharp of A is this pure expression. So that's a very simplified account of their paper. So and again, some more details, but again, still pretty much simplified. So the idea is to start with two functions that are constructive. So there's interpretation, which takes an A, an abstract value, and returns a set of concrete values, as usual. And then there's extraction, which applies to a single concrete value, not a set of concrete values, just a single concrete values, and should produce an abstraction. And a key observation is that this extraction must be computable. For instance, if you need to abstract constants, you are analyzing expressions, and you have constants, you need to have something like nu to find the abstract value corresponding to each constant. Okay, and so from there they derive a Galois connection of a particular shape that I didn't know. So it's between sets of concrete things and sets of abstract things. So for instance, for the even odd parity domain, that would be subsets of even and odd. Okay, why not? But I don't see how intervals fit in that, so I'm a little bit uneasy, but never mind. So you can define alphas and gammas in the trivial way, and as a monad, they use the classical infinite non-computable sets, the functions from X to prop, basically the membership function of the set. As opposed to computable finite sets of A's, lists of A's, for instance, which are the arguments and the results of abstract operators. And maybe it's a little too small, but so that's taken from their paper. So to the left, you have a calculation on paper in their monad, in their domain, sorry. And to the right, you have the same calculation that's being mechanized in AGDA. So that's really a tour de force, as we say in French, because AGDA has no interactive proof mode, but they actually implemented one. So what you see in pretty small on the right, the do, the brackets, the curvy brackets, etc. These are all terms, AGDA terms, that explain how to refocus and unfold and apply simplification rules and so on. So this is completely crazy, if you want my opinion. But no, not crazy. Black magic. This is black magic. Okay, but in the end it works, and it looks a little bit like the original on-paper derivation. Okay, and if I have 5 more minutes, no. Then the plan M can be turned into a plan U like universes. In a system like Coq, so you can use monads. Remember, the original motivation for monad was to separate effectful computations from pure computations, but in some other languages, you do that with a type system. Okay. For instance, in Java, there's throws clauses and methods. If it's there, it means a method can throw exceptions, and if it's not, then it cannot. And in Coq and Lean, there's something a little bit like that. In their universe structure, the universes are types for types. And so they have two major universes, prop, which is a universe of logical propositions, and then that can have proofs, and type, which is a universe of data types and their computations. And various combinations are possible. This is very simplified. Various combinations are possible, but there's something very important, which is that a computation in type cannot depend on a proof in prop. And for instance, if you have a proof of this Turing machine terminates or it does not terminate, which you can get with an axiom, classical axiom, for instance, we can reason by case whether the Turing machine terminates or not, which is very useful, but we cannot define a Boolean values, it terminates, where you give it the proof and the Turing machine, the proof, and it says yes or no. Actually, all functions that have this type are constant, okay, because they cannot, the bool, which is in type, cannot depend on this proof, which is in prop. And the good thing about this distinction is it makes it possible to add excluded middle or other classical axioms without endangering extractions. Extraction that erases everything that is in prop. Okay, so that's pretty cool. And so if you want to do the plan U in Coq, so I tried to do that while preparing those slides. So you can define alpha as a relation between sets of concrete things and abstract things A. So this is the parity abstraction, so there will be 4 cases, bottom, even, odd, and top. And it's just a relation, okay? Nothing is computable in there. You can show that it satisfies the adjunction property. So it's a good alpha, if you want. You could say, okay, let me use a choice axiom or a description axiom to get an actual alpha function from this predicate. But actually, it leads nowhere, and it can endanger extraction. So let's not do that. Let's stay with relations. You can describe abstract operators with the help of is_alpha. So this is slightly tricky, but the idea is to show that for any A, which is the abstraction of the argument, there exists in type an A prime, so we can actually construct an A prime that satisfies this property. A prime is the alpha of the set, of the image of gamma of A by the successor function, okay? So this is the closest I could get to the equation, so sharp equals alpha suc gamma. And now you can use interactive proof mode to construct A prime. And now, in the end, you can project out the abstract operator and its soundness and optimality proof as the two components of this kind of dependent product. So it's not super pretty, so this is the proof, the derivation for successor. Of course, there are 4 cases, but top, even, and odd. And in each case, so either I just invoke theorems and the corresponding value, but top, pops out of the theorem, or I actually say it explicitly. Okay, so it's not super pretty, but it's a step, let's say, towards some kind of calculation. So as I say, it's kind of a Pyrrhic victory for mechanization. So in the end, it is possible to mechanize some forms of Galois connections. That could be Darrell and Van Horn's eta mu, or the is_alpha gamma presentation, as I just showed you. Use that to calculate abstract operations, but the mechanized approaches don't have yet the crispness nor the immediacy of the classic pencil and paper presentation of AI. So what's next? This is the next 40 years, after all. And I'm not sure I have much to say there, but a little bit. So coming back to the first half of my talk, the formal verification of static analyzers, I think this naive, gamma-only abstract interpretation provides a robust approach. Okay, all you want to do is prove the soundness of a static analyzer. That will work fine. That's now textbook material. I mentioned the concrete semantics book. It scales to non-trivial analyses, including relational analyses, as we demonstrated in Verasco. It's perhaps hard to scale much further because algorithms get extremely complex. I don't know if Jérôme Ferret is here. We briefly looked with him at filter domains and then ran away. It was just too hard. And as I said, there's not that much interest actually for verified static analysis outside of compilers. And now on the mechanization of abstract interpretation, as I showed, it's still a challenge for contemporary proof assistance. And that's actually interesting. I believe abstract interpretation is deeply grounded in set theory. So it's not just that Patrick and Radia liked modern mathematics in the 1970s. I think there is something deeply set theoretic, just like there is something deeply order theoretic in Scott domains. Okay, I can't quite put my finger on it, but there is something set theoretic. It's not just a 1970s fashion. Yet, at the end, it produces algorithms, and that's where things clash, basically, and that's where it becomes interesting. And then contemporary proof assistants have poor support for the calculational style, and it's not just for Patrick's derivation, it's also for Bird style, Richard Bird style program derivations, for instance. It's also for undergraduate mathematics, okay, when you do equal blah, 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 equal blah, 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 equal blah, blah, blah. So there's probably something to do there independently of abstract interpretation. All right, and so just to conclude, that was the first 40 years. Now, the next 40 years. Actually, this morning, I took the tube, and I saw also there's you can extend to 160 years if you want. Thank you.
So we have time for a couple of questions.
Yeah.
Yes, David.
So you mentioned certificates of correctness for certain abstract domains. At some point, we investigated certificates of optimality, but then people lost interest. It was difficult to find students. This would mean that the interpreter would be partially correct because it could fail to show. Would be partially optimal. You would have to put everything in a monad or something like that. What do you think about that?
I think it's generally useful. The VPL, your Verilog polyhedral library, we try to use it in other projects where actually having optimal results would have been good. Proofs of optimality would have been good. So I think it is great in general. And the possibility of failure during analysis, I think it's not too serious. I mean, at least the user knows what's going on. Okay. But practically, it's not that much different from just returning top and then making alarms. Well, it's a little better, let's say. It's an alarm with a better diagnostic. The problem is probably not in your code, but it is in the analyzer. Patrick.
I do my computation by hand, I think, to make Maple
Uh-huh.
style of thing. And I was wondering, would it be possible to have a tool which is both Maple and code, that is where it's essentially rewriting, and at some point you have to have a proof, which is a bit more difficult, but most is rewriting and things like that.
Okay. So you can do proofs by rewriting in Kirk. It's certainly less convenient than in Maple or systems like this. And but yeah, there's a growing interest towards formalizing like undergraduate mathematics in Kirk, so they will have to provide a more Maple-like experience. There's no way around that. But yeah, Kirk and those systems are more oriented toward deductive proofs. Yes.
So my understanding of how people work in Coq is or some will, based on software foundations, is that you'll often define what I'd call a procedure, and they would call a function, and then a relational counterpart to it.
Yes.
And then you work to kind of show the two together. Are there, in general, techniques for just starting with relations and then somehow turning to something that's extractable as a procedure without having to do the work by hand?
That's an interesting question. I don't know of any off the top of my head, but this is such a natural thing to have that probably someone has looked into this. So let's discuss that at the break. Molly.
I have 2 questions.
Oh, not sure we have the time budget.
It's more pragmatic. Like when I work of functional interpretation, usually, especially in point analysis, every time I try to prove that algorithm to be sound, I found a bug.
Okay.
And it's including references and my own, unfortunately. So when does this happen to you? In this proof, you are finding also bugs?
Oh, I'm pretty sure. Well, so my experience is just with the data flow analysis of CompSert, but yeah, I found a bunch of corner cases, and as you say, it's not so much with numerical abstractions, but very much with pointer and memory state abstractions. Those can be super tricky, especially with the CompSert memory model, the concrete model, which is not trivial either. It's not just a mapping from locations to values. So yes. When you try to prove things, you find bugs. That is true. But maybe not very serious ones or bugs you don't often run into. But that's also why it's good to test and to prove at the same time. Of course. In the end, there's no admitted or whatever in the 30,000 lines in the end. Second question.
More technical. I love the calculation of one, but I'm trying to understand in the work that Tom Epps and Dennis Copan and Greta and I did. I don't know if you know this connection, alpha from below, alpha from above. So your work seems to be what we call alpha from below. Do you know the difference? So we connect calculational.
Mm-hmm.
Logic, classical logic to absolute interpretation. POV formulated in logic to absolute interpretation.
Okay.
And the idea is we have 2 mechanisms. One is that you iterate from bottom, and the other one is you iterate from top.
Okay.
You only iterate from bottom.
Yes. We do only iterations from bottom. Then that is correct.
Does it make sense for you also? Because we find in
That's an excellent question, actually. I don't think we discussed that during the project, but okay. So yeah, we didn't think of that. So I won't be able to answer your question. All right.
Thank you very much.
Thank you.
So our next speaker is Kwang, and let's stop this week.
Okay. How to make it okay. 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 Right. Okay. Thank you. Thank for the inviting me for this meaningful workshop. My name is Kwang Lee from Seoul National University, Korea. And let me start with these 3 photos. Rightmost photo is our group, and actually left 2 photos that I took when Patrick and Radia visited us. First photo was about quarter century ago, almost. And when we invited him, I was not lucky enough to be ENS student to learn abstract interpretation from Patrick, but actually we were brave to invite him over to Korea to give a 1 week, 9 to 5, 5 days in a row, full tutorial about everything about abstract interpretation. That was, and the first photo was one that I took him when he was in my office at that time. And it was unforgettable 1 week memory. Okay, and the second photo was we invited Radia and Patrick again about 10 or 15 years ago as a departmental distinguished lecture, and also to celebrate the opening of our research center. Yeah, at that time we were fortunate to have a very generous grant from Korea Research Foundation. Okay, so in this talk, I'd like to share with you what we have done for program analysis and also for program synthesis based on abstract interpretation. And the title of this talk is about program synthesis that I worked with Yong-ho and Woo-seok. And actually, the synthesis part will comprise 2/3 of my presentation, and the remaining 1/3 will be about the brief review about what we have done for analysis part, okay? All right, so our story of abstract interpretation. So 2 parts, analysis and synthesis. So for once upon a time, after we learned from Patrick about abstract interpretations and so on, we became curious whether we can build a realistic analyzers to find some real bugs in real C programs. So we ventured out to build a static analyzer based on abstract interpretation framework for almost full set of C programs. And I said it's more sound, so it's more sound than less sound one. So it has we try to have as little assumptions possible about the semantics of C. And after we built this workshop, we tried to experiment it with against some open source C programs and Linux, some device drivers of Linux and so on. And we found that the tool can really find some meaningful bugs. So we are excited. So after that, we branched it to why not commercialize it. So it has been more than 10 years, and now the company become a bit stable. So now they boast about static checkers for safety and security errors for more than 25 programming language. And on the way of commercializing it, as you all know, we had to give up lots of good things about the soundness and so on. So lots of compromises happens there. So we had a very hard time to commercialize the Workbench version into a commercial product. And one branch was that. After that, we decided to come back to the academic university lab, and we scratched our head that without those compromises from the beginning of the Workbench, that is a global sound analyzer for C programs, we are curious of how much we can do about the scalability and the precision of the analyzer. So we managed to come up with a interesting framework that we call it SPAS analysis framework that can improve the scalability without any compromise of the soundness of the analyzer. And after that, the second part is about what we can do about precision. Okay, so we'd like to have a cost-effective way of improving the precision without again compromising the soundness and so on and so forth. So we managed to come up with some interesting solutions that we like, and everything was available in the open GitHub. And that was our story about static analysis based on abstract interpretation from an angle of abstract interpretation in practice. Okay. And after that, more recently, we also doing interesting work on program synthesis based on abstract interpretation. So thanks to abstract interpretation technique, we achieved a superb performance in program synthesis. They can beat other competitors. So actually the underlying abstract interpretation technique is fairly simple and standard thing, like a bidirectional analysis, forward and backward analysis. And we are using a combination of domains and something called the reduced product. And sometimes we do a finite refinement, kind of abstraction refinement, and so on and so forth. So using those three very standard, simple-minded technique that has been born in abstract interpretation, we can achieve nice performance in program synthesis. Okay, so I will present the synthesis later, and before that, I will give you a brief overview of our analysis things about the sparse analysis and selective extensivity things. So this slide is about commercialization. Okay, so actually the colorful figures are the snapshots of the company's web homepage, and they are boasting about advanced static analysis and so on and so forth. And actually those are based on our lab workbench that has been developed on the abstract interpretation framework. Okay, so the point of this slide is the last line. Thanks to abstract interpretation framework, we were able to build a realistic global analyzers for the almost full set of C programs, and based on that, they are doing kind of commercializations. Okay, that was very nice. And after that, as I told you, we came back to a lab, university lab, and we tried to understand. We tried to see how far we can do for scalability. So, given a sound and global version, and we managed to come up with a we call general sparse analysis framework. And by using that one, just look at the graph there. The performance improvement is very impressive. It's almost like an exponential improvement in scalability we achieved. Okay, and we dare to say general because it's based on the abstract interpretation framework. Okay, yeah. So at the time when we we were able to analyze the globally analyze a C program from the main procedures. 1 million lines in 10 hours in the usual laptop machine. Okay, that was the performance at that time. The idea is that we tried is to exploit the semantic sparsity. By that I mean there's two sparsities in the semantics. One is a spatial, we name the spatial one, and the other one is a temporal sparsity. And spatial. Okay, I will briefly give you the intuition about the spatial and temporal sparsities later. And before that, our framework is like this one. Given an abstract semantic function f sharp, we give the guidance how to make it sparse. Okay, so sparse, and still we can guarantee that the original the analysis accuracy is preserved after the specification. That was very nice. And actually, the point of this slide is this one. After we report this result to the community, and one comment that I like is this one. The theoretical result is very general, thanks to abstract interpretation, because everything is in top of the abstract semantics. And it could be applied to many other analyses. PLDI papers have been accepted. That was simply instances of this framework. So this was quite a thankful comment. And again, we achieved this one because thanks to the abstract interpretation framework. Okay, and the idea of this spatial and temporal localization is fairly simple. Let's focus on this graph. Suppose the straight line code of C-like programs, and actually the blue boxes. Okay, so we are doing a flow sensitive analysis for each program point. We try to estimate the machine state of C programs, and in each machine state. Let's focus on the blue box. We try to record the memory map that can happen at the point during the executions. So this program has 6 memory locations. So for every program point, we record the whole machine state, and that is actually the waste. Because let's focus on the orange box. Because at each statement, the statement will use only a small part of the memory state. So we don't have to record everything. Instead of that, we can just record the orange box that is small, just a fairly small portion of the whole memory state. Okay, so that is what I mean by spatial localization. So it's reminiscent of in the separation logic, frame rule, that kind of thing, or in static analysis, the abstract garbage collection thing. Okay, so each program point we just record the small portion of the machine state. That is enough. And about the temporal localizations is that we don't have to, during the program analysis, during the abstract interpretation, we don't have to follow the sequence that is explicit in the program text. actually it's enough to follow the semantic dependencies. So instead of following the black arrows that is explicit in the program text, we can just follow the express line, the orange arrow. That means that after we define the x value over there, then the result state, we don't have to pass it along the flow in the program text. We can just pass that newly defined x image to the next use point. Okay, so that's what I mean by temporal localization. So we can use these two kind of sparsity in the semantics, try to fully exploit it to make our analyzer economical as possible. Okay. So we achieved that impressive performance improvement by this framework. And then after that, we scratched our head again to how to improve the precision in a cost-effective way. Okay, so actually we kind of this is a kind of exaggerations, but anyway we try to improve the precision thing. And our idea is that we can apply the precision improvement technique only selectively. So precision improvement here is not applying a different, elaborate domains. No, given an abstract, we just focus on the flow sensitivity and context sensitivity. So instead of blindly turning on the sensitivity for every function call, we try to selectively apply the context sensitivity for a particular function calls only. If that sensitivity improves the accuracy of the final result. Okay. So the idea is, the diagram says that, okay, so the blue, the star is the actual set of program state, and the green one is an over approximation that we compute during the program analysis. And suppose the red blob is the error state. And instead of improving the accuracy for every corner that is costly, it's enough to improve the accuracy just around the error state area. Okay, that's the key idea. And our method achieved this interesting performance number. We pay 28% more to reduce the 20% false alarms. Okay, if you do the blind, naive context-sensitive analysis, for example, 3 CFA, 3 CFA, and the performance cost increased about 1,300% more, just to reduce that similar size of the memory false alarms. Okay, so we designed. So the question is that, how do you know which function call we have to turn on the context sensitivity? That is the question. And then before the analysis, we'd like to determine it. Okay, so it's kind of catch-22 situations. To analyze very effectively, we have to analyze the future of the impact of the context sensitivity. Well, the solution is a very simple one. We just design a pre-analysis. Okay, so that pre-analysis is that we put the context sensitivity as high as possible, say 100, whatever. But we are using only 2-element domain, and that 2-element domain basically says that, okay, no effect. Okay, just analyze, just apply the pre-analysis. Then each function call, it shows that, okay, this is good one. This one you don't have to put on context sensitivity and so on. Okay. And again, thanks to the AI framework, it's easy to define that kind of pre-analysis, right? And we apply that one. And later, we also try to apply the machine learning technique, Bayesian optimizations, for linear score function that scores the context-sensitive effectiveness for each function call. And depending on the score, we turn it on and off. Okay. So actually, in order to do that, design. So side cost is that, okay, we have to design the new analysis, the pre-analysis, or we have to train the analyzer for Bayesian optimization to figure out the linear score function. And actually, having a pre-analysis design to us, it was easier and quick. Okay. So this is the thing that we have done for developing a static analyzer, realistic static analyzer for C programs, and having some interesting, drive to improve the scalability and precision improvement. And we come up with the interesting techniques. Okay. So this is it. And now, from now on, I'd like to show you our most recent works that we have done on program synthesis. Okay. So the target of the technique, synthesis technique is the inductive synthesis one. The input is a grandma, and the input-output pairs. And the output of the goal, we need to have an automatic program that automatically generate a right program in the grammar that satisfies the input-output pairs. Okay. So, for example, this grammar is a bit manipulation expression grammar. X is an input. 0001 is a 4-bit binary string constant, and shift and or exclusive or blah blah blah. Okay. And then second input specification is an input and output. 1011, and it must return 0011. What would be the function? There can be many, right? But we come up with the goal is that to try to have a fully automatic system that build this output. So believe it or not, this function will generate the 0011 given 1011. Okay. All right. So this is a setting. So actually, the automatic synthesis examples, the tool that we developed, I'd like to impress you with some examples. So bit manipulation operator syntax, given a 5 to 20 input-output pairs, it can generate within 1 second or up to 35 minutes, can generate these functions. See, given a 8-bit string, it can generate the absolute number. Believe it or not, that bit manipulation function does that one. And it can generate that procedure, that expressions by program synthesis. And sign function is given a 8-bit string, whether it's positive, negative, or 0, it can generate, by using that operations, it can return 0, -1, or 1. Without using any if branches, there's no case analysis. So this is very tricky, interesting thing. And average floor, average ceiling with the unsigned 8-bit, this function is automatically generated by given a 5 or 6 or 7 input-output pairs. Very interesting. And another thing is that one interesting application of program synthesis is de-obfuscation. Given a very complicated obfuscated program, we can generate the input-output pairs, and then we feed the input-output pairs to our system, and it can generate a more readable program. Okay, so it's kind of de-obfuscation. So actually, the last example was the one that took 35 minutes, given 20 input-output pairs.
The way you do the last one is that by taking the obfuscated program and run it like 20 times, you get
collect the input-output, and then feed it to okay. Yeah. Yeah. All right. So this is the thing, and actually our system, we name it Simba. The x-axis are the number of other competitors, including ours, and the y-axis is the number of solutions that can be generated within the same time bound. And our performance is very, very good, thanks to abstract interpretation techniques. And as you see in the followings, the things that we use is a very simple thing. Very simple 3 techniques in abstract interpretation. Okay. So synthesis key is how to prune the huge search space. Okay. So given this bit manipulation syntax, and given this input-output pair, what we do is a kind of hybrid of top-down and bottom-up. From top-down, from the beginning of from the S symbol, okay, non-terminal symbol. Following the grammar, we expand it, and at some point we stop, and then we're using some constant things, we compose some small expressions and try to plug into the non-terminal symbols and see if whether that satisfies the given input-output pairs. Okay. All right. Now, as you see, the X is definitely not the solution because 1011 returns different one. Okay, so it's not an identity function. Suppose the second X marked subtree, X shifted by some expression. And then we know that before expanding further, before we search more, we know that, X shifted by something cannot satisfy the input-output pair by any way. Whatever expression we plug into that box, there's no way that satisfies that input-output pairs. So the interesting cute analysis problem is that given a partial program with a one more holes in a program, we try to understand the possible value and see if whether it can satisfy the input-output pairs or not. All right, so naturally we do both. As you see, we are very fortunate in a sense that this grammar does not have any loops, no function calls, no if branches, and very simple bit operations only. Only challenge is that there's one or more holes in the program. Well, analyzing that possible value of that one is easy because we can just assume that the box can be any value. So assuming that the input is a 4-bit, so forward analysis, we can, given a input, particular input 1011, we can conclude that the value of the output would be, this one would be top, and join the O operation, we can generate the one top one. It's very simple. And we know that, that cannot be 0011. So definitely we have to stop expanding those partial program anymore. So discard it. But forward analysis is not complete enough. So for example, that slightly different partial program, X, exclusive OR, and box. Okay, and we'd like to see whether we have to continue exploring the subtrees or not. And by the forward analysis, the conclusion is that, X given 1011, X exclusive or something that we don't know, they can generate the top. So no information. So there's no trimming is possible. So because we know the output, we can do a backward analysis too. So it's also easy because the syntax is a fairly straightforward single line of expressions. And given this output, given this partial program, we do a backward analysis and we come up, because X is known, and we can conclude that the box must be 10000. Okay, and then when we expand this box with different expressions, we can some subtrees we can trim it. Because this part, this expression is for the box, and box value must be 1000, but there's no way to make this expression become 1000. And divided by this box cannot be this one either. So we can safely trim the stop exploring the left two subtrees. Okay. And so the forward and backward analysis was fun to do, and we can trim some subtrees during the search phase. But it was not enough. And also in competition with other tools that does not use the analysis, but using a collection of heuristics, but very quick to explore very huge space. So in competition with those tools, the time constraint is very short, because if we spend more time in analysis, then we lose. Okay, so our analysis must be very quick, and would like to be very as precise as possible. And we found that for the backward analysis, is not enough. And we have some time budget still remains. So we try more. And that is that we use the different domains and try to refine the results of each other's. Okay, I mean, in this audience, I think you know all this. And we found that just the bitwise domain and unsigned interval and signed interval, 3 domains are enough to improve the accuracy a bit within that time budget. And the bitwise domain top 10, and suppose we come up with in the interval domain 06, then we can refine each other. Okay, we refine each other, and we come to the top 10 and 15. Okay, so we improve it a bit together, and we are using that one too. And still, we improved a bit more, but we figured out that there's still some time budget remains, and we'd like to do more. And at this time, we'd like to some kind of on-the-fly refinement, finite refinement. And in this case, bit thing is only 1, 0, and 1, so always finite. So we can do abstraction refinement. So for that partial program, we do forward analysis. There's nothing we can gain. By backward analysis, we can collect some more information about the box. Box must be top 1. Okay, and on the way of doing that, we think that we can do refinement at this point. So instead of trying 0 top 1, we can finite concretizations kind of thing. It can be 0, 0, 1, 1 or 0, 1, 1, 1. Okay, so we try to figure out what would be the value of a box for that expression to be 0, 0, 1, 1 and separately 0, 1, 1, 1. And we come up with the 2 solutions of box, and then finally single solution for box would be the join of those 2 solutions. And by doing this, we can improve the information of this bit from top to 0. So very small improvement. And it also helps us to improve the accuracy within the constraint of the time budget. So using this fairly standard and cute applications of the 3 techniques in abstract interpretations, we were able to beat the existing program synthesizers. And we built the whole system. And this graph shows that the top graph is the same as the before in a colorful manner. And actually, that is the graph that shows the number of the fastest solved problems of each domain. So it shows that our tool Simba was very quick to zero in on the solution. Okay, and the bottom graph shows that given a 1-hour budget, actually other tools can catch up, but still absolute number of solutions are less than ours, except the comparable cases of where we try to build a bit manipulation program with condition expressions. Then it's okay. So this is my story, open abstract interpretation and analysis and synthesis. In analysis, we try to do some kind of limit that we think interesting. One is commercialization. And the other one is on the sound and global analysis workbench, we try to improve the scalability. What techniques we need to improve the scalability and cost-effective precision. And synthesis part, we're also using fairly standard, simple techniques in abstract interpretations to achieve a very good performance in program synthesis for bit manipulation programs. Okay, so in retrospect, I think this is definitely true. At least for me, without AI frameworks, without understanding, knowing, having this framework and concept or vocabularies, we might have failed to conceive and develop our methods. Okay, I've been too scared of the sheer complexities of the reality. The C programs, I don't think if we didn't understand, you didn't know the abstract interpretation framework in the beginning, we couldn't imagine to build a static analyzer for the full set of C. That was definitely true. And so So without having that knowledge, having that mindset, maybe even though we try to build something, maybe we have no understanding of what we are doing, and therefore we fail to communicate our message to the community. So, okay, so this is it. Thank you very much. All right.
Do you have questions?
Yes.
Thanks for the great talk. I'm wondering, in your top-down synthesizer,
Yeah.
It's possible that you could generate some programs like Box, XOR Box, or something where there's really very little that an abstract interpretation can do.
Yeah.
How do you decide when to run your interpretation, or do you somehow avoid generating terms that are too?
Yeah, the term must contains only, usually contains the input variable. It helps a lot. Yeah. We can still do something. No. Okay. Yeah.
And you mentioned that there was also a bottom-up.
Yeah. Yes.
Portion. When
Yeah.
do you switch it? When do you decide? How do you decide when to switch it?
Oh, actually, what you do is that we do an expansion up to two phases, and then we try to fill it up. Yeah. And yes.
In one case of these synthesis examples you showed, how many times would you invoke the abstract interpretation during
Oh,
such a run?
I don't have that number.
Oh, but what magnitude?
It was very quick, less than a second. So,
But you must run the abstract interpretation.
oh yeah, the analyzer. Oh yes, oh yes. Oh, I don't know. Really, we didn't measure. Yeah.
But it seems like there's a basic idea of abstract interpretation of partial programs.
Yes.
A lot of times people do abstract interpretation of complete programs.
Right.
But this is
Yeah. That's what I say. It's a cute problem. Yes.
Two questions. Are you guaranteed to find the smallest program or
No.
shallowest program?
No, there is no such guarantee.
And did you try it for other domains except just bit manipulating?
Yeah, this is the first one, and we try to work on string manipulation program. But for string domain, the backward analysis is fairly complicated. So we sort of discouraged.
Thank you.
Yes.
There's a microphone. Just behind you.
Oh, okay. Hi, thank you for the talk. Just a simple question on the scalability part. You said that for sparsity, you kind of analyze where, for example, in the first node, the memory state you will use, and then you can scheme support.
Right.
I just didn't
How
get what you do. Is it a syntactical analysis there?
Oh, okay. So actually, this is again the kind of catch-22 situation. Before we do this kind of sparse analysis, we have to know beforehand for each portion of the program what memory locations will be accessed. Okay, so what do you do? Pre-analysis.
Yeah, and so my question is it a syntactical one, semantical one? Because I don't know if a semantical one in big project could just slow a lot the analysis.
Yeah, this one, the example is fairly straightforward. It's explicit from the program text, but for arbitrary C expressions that follow, lots of pointers and so on and so forth, we have no idea from the program text which memory location will be accessed.
Okay,
yeah,
thanks.
we have to do some kind of analysis.
Okay, thank you.
Yeah.
Any other question? I may have one.
So you have a static analyzer, and then you did program synthesis.
Yeah.
Can you synthesize a static analyzer?
No, I don't know. I don't know. Why not in 10, maybe 20 or 30 years? Yeah. We tried ChatGPT.
Oh.
No future yet. Fortunately. Yes. Yeah, actually we tried. We tried some simple examples, and they gave a random program. They gave a completely random program. Yeah. So, you can try it. Given this grammar and.
Can you use it as a first guess that you can refine then?
First guess? What do you mean?
I mean, it has some intuition, but it's wrong. But then it leaves you on the good path.
The input-output pairs. Oh,
so
I see.
you use it as a, as a guest, and then you.
Yeah,
you
I tried 5 or 6 times interaction with the ChatGPT to guide him, but still it generates a random code. So I forget. Yeah.
Yeah, just I'm very naive with program synthesis, so I just wonder what it will involve to just expand the grammar with other construction and like loops and conditional branching.
So your question is, how do we expand?
Yeah, what will it involve? I'm very naive to the domain, so.
I mean, given this one, we do not use any heuristics. We just blindly expand breadth first.
No. It was about expanding the grammar, like handling other
using
kind of program. Yeah.
Oh, I see. Yeah, we are very careful, because if the program has an if or loop, then how do you do the backward analysis? Do you know how to do it precisely?
Depends on the kind of analysis, I guess.
Oh, okay, maybe.
Yeah, I don't
maybe,
know.
yeah. It's a challenging thing, right?
Any last question?
So maybe I have one last one. Sorry.
Oh, okay.
Yeah, sorry. So when I look at the formula that has been, synthesized, it seems very similar to an old book that we read a lot, which is called Hacker's Delight.
Yeah, exactly.
Yes.
Yes.
Have you compared?
Exactly. Oh, yeah,
this
Actually,
kind of stuff.
Exactly. Actually, the benchmarks. One of the set of benchmark is the Hacker's Delight.
Oh, okay.
Yeah, that's the. Yeah, I think these are from Hacker's Delight. I think.
A follow-up question, because so some of those formulas are very much Hacker's Delight-like. However, x shifted by x is really strange, because it's defined only for pretty small values of x, like between 0 for 8-bit numbers, maybe between 0 and 7 or something like that. So that's something you will never see in Hacker's Delight. So what semantics do you give?
I thought these are in Hacker's Delight, no?
No. What semantics do you give to 128 shifted 128 times?
I mean, it's a very naive definition. The shift
okay,
2
so
arrow is just
zero,
the usual, shifting, and 3 arrow is the shifting that preserves the sign bit.
Yes, but what if you shift by more bits than you have
just
in the number?
Just to keep shifting, and it generates the 0000.
That's not defined in C and in most actual programming languages. So there's something a little bit fishy with those x shifted by x formulas. It depends a lot on the semantics you actually give to the shift. That was my only observation. But yeah, the average formulas are just wonderful.
I thought that this is the exact solution that appears in the Hacker's Delight.
I'll check.
I didn't check either. Okay.
Now we have a break, and the break is on the 3rd floor, I've been told.
a chairwoman who is actually putting down chairs.
Okay, all is good, right? Okay, great. So we have two more long talks in this session. The first one is Jens Foxberg.
Good morning. Quantum algorithms can solve problems exponentially faster than classical computers, and the quantum computers that run them are getting faster. And as it happens, simulation of quantum programs of, I would say, more than 50 qubits, that's already infeasible. And as it happens, if you, let's say you go to 300 qubits, then at that point, we already are working with more complex numbers than in the known universe, that are atoms in the known universe. And so the question is, how can we verify anything about quantum programs when we have such big state vectors? And so, so I'm here to persuade you that abstract interpretation can verify assertions statically about quantum programs. And so what I will do is that I will introduce quantum computing and try to explain why the problem is hard. And then I will build a Galois connection. And then I'll show an example and some experimental results. And so this is a qubit. It's a two-dimensional vector of complex numbers. And as it happens, it's a unit vector. And so that's what quantum computers work with, unit vectors of complex numbers. Very big unit vectors, much bigger than this normally, than just a lot of complex numbers. And so, so you can see the idea here is that every time we add a qubit, we double the length of the vector. And so it stays a unit vector, so all the numbers in the vector kind of get smaller. But so once we add 50 qubits, even like the biggest supercomputer in the US has trouble keeping up with simulating this stuff. If you go to 64 qubits, we have as many complex numbers as there were grains on the chessboard in the old story about you double the number of grains. 300 qubits, now we are up to the number of atoms in the universe, actually more, unless the Webb telescope is like expanding the known universe, I'm not sure. And IBM Osprey is a quantum computer that came out a year and a half ago that has 433 qubits, and it's growing fast. And so just enormous amounts of stuff. And so what quantum computing does with these unit vectors is linear algebra. And its reason why it's linear algebra is actually thanks to John von Neumann. So we're really computing with quantum mechanics, but there's an interface to quantum mechanics stated by John von Neumann's 4 axioms that says that the state vector is a unit vector of complex numbers. The way we do a computation step is to apply a matrix, and then we can get partial information about the state. We cannot just print out the state vector. That would violate laws of quantum mechanics, but we can get to know something about it. And so this means that the big picture is like this. A quantum computer is or will be, maybe, hopefully one day, an accelerator in the same sense as a GPU or a TPU or an FPGA or whatever these things are. So that means something where there will be a CPU that's still running the show, and then when it has a task that's fit for a quantum computer, it will take some bits, load them up as qubits for the quantum computer can then run, and then we can then what's normally called measure and get out some bits. And so that means use the quantum computer for what it's good for. And so that's kind of what the field is working on. The hardware people are building better qubits, and the software people are trying to learn to program this. So here's an example of what things normally look like. So we have a vector in normal notation on the right, and then the way the quantum people like to write such a vector is on the left, which is, so they use these brackets here. And so those are both 4-dimensional vectors. And so actually, so this is called Dirac notation after Professor Dirac, where this thing here is a vector that has a 1 here and zeros. And this vector here has zeros and then a 1. And as you can see, it works out to be a unit vector. And one can produce this vector by this thing here, which the quantum people will then call a circuit that says we start with both of the qubits being, so now there's just 1 qubit, so this is like a 1-0 vector and a 1-0 vector. Here's a matrix, and if you execute those correctly, you will get this state. That's kind of what the quantum algorithms people are doing all day. They're writing circuits like that to try to get things done. So the quantum computers, of course, should be fast. So there's this major question of what can a quantum computer then do in polynomial time. And so I just want, so just want to give you a sense of how this looks if we just take a complexity angle on this. So here's what a classical computer can do in polynomial time. Here's what a quantum computer can do in polynomial time. Here's what a classical computer can do with sort of non-deterministically polynomial time. And this is kind of non-deterministically quantum polynomial time. This is if the verifier has a quantum computer. And then you can sort of, it's always like seems to be more. But it turns out that once you get to the p-space level, then sort of quantum and classical coincide at that level. But nobody's going to really care about this except theoretically. All the interesting stuff is down here. So what is it then that we can do in quantum polynomial time? So maybe I should just add one more thing about this picture. So you know that so people sort of care about whether p is equal to np for many reasons. Now there's another big question whether PQP is equal or what it is, contained or containing NP. So that's like a second major problem that's driving the complexity people nuts. But for what it's worth, what we can do in sort of quantum polynomial time is, of course, Shor's algorithm is famous for being able to factor integers in polynomial time. Then there's the original motivation for quantum, which was Feynman started to talk about simulating quantum physics and quantum chemistry on a quantum computer. That's kind of what really sparked the whole field to work on that vision. And that problem, as it happens, is complete for quantum polynomial time. And so that's a really good one. And then another example that the US government is putting a lot of money into is essentially SAT solving. So solving NP-complete problems in approximately in quantum polynomial time. So there's this algorithm called QAOA, the quantum approximate optimization algorithm that the government is putting a lot of money into. So one can wonder, okay, so when is this going to become real? And so I'm just going to sort of list some breakthroughs that we need to get there. So I would say quantum is at least 3 breakthroughs away from being commercially viable. I'll just tell you quickly what they are. So here's how many qubits quantum computers have today, or sort of the last few years. I just took Wikipedia and plotted them. The IBM Osprey is up there. That computer is somewhere at USTC in Hefei in China. And some of the other ones have fewer qubits. So you can see that we sort of, there's the trend line. We're sort of adding a qubit per month or something like that. I think these guys have to pick it up because we kind of need a lot of qubits. And the reason we need a lot of qubits is this number here. So the reliability of a single operation on a quantum computer today is like this, and that's on a good day. A lot of quantum computers is like 99.9%. So you can imagine if you do 100 of those in a row for just a small program, there's like no reliability left at that point. And so what does this mean? It means that we need error correction. And so current wisdom of error correction is that we need, for every qubit that we want to be 100% good, our operations work 100% correctly, we need 1,000 support qubits. And so there was a time when Google on their webpage said, we will by 2035 build a quantum computer with 1 million qubits. And they have kind of taken that off their webpage again. But for what it's worth, that would mean 1,000 perfect, wonderful qubits, and then almost 1 million support qubits to make that happen. So, so these people who build qubits, they need to, they're slacking off as far as I'm concerned. They need to build more qubits and fast. I want to say, though, that it seems like there's a revolution in quantum error correction coming. So I've been talking to people quite a bit about that. And there's this new thing called low-density parity check codes that are coming up. And the people are expecting that within 2-3 years, we're going to get rid of all the old codes, and we're going to use the new ones. And these this sort of expectation of 1,000 helper qubits is going to go well down. So we shall see. Okay, so there is another problem, a third problem, which is coherence time. And so the truth of the matter is that quantum computers are kind of slow in the following sense. So there are many different technologies. So if we work on an ion trap computer, the current continuum ion trap computers, they execute like one operation, so one of these matrix operations, in like 1 microsecond, maybe 2. If you look at this IBM Osprey, that's a superconducting quantum computer. It will maybe like 10 nanoseconds, 100 nanoseconds, so faster. But the problem is, if you're going to do quite a lot of these operations, you need the computer to stay good. And the truth of the matter is that computation here for the technologies we have today happens at something like maybe 0.015 Kelvin typically. So everything is like lying completely still. And at that point, we can control stuff, like control individual electrons. And it doesn't work perfectly. You know, at some point, the second law of thermodynamics is just going to get after you, and things fall apart. And that's where error correction comes in to then like keep it going. But the question is, how long can we really keep this going? And so we need that breakthrough to be there. Today, I think coherence times are in seconds for the best technologies, tens of seconds if they really work hard. They're very optimistic that they can get that up to hours, but okay. So for what it's worth, so then let's return to how hard is verification. And so here's a statement. So you see I'm talking about QMA completeness, which was in my picture before. So that's like quantum NP, if you like. And so what this theorem here says is that even knowing whether a quantum circuit's full of qubits and gates and stuff everywhere, knowing that it implements the identity function, that is QMA complete. And so that in this world here, given how big everything is, that means completely intractable. There's no fast SAT solver that's going to come and help you here. And so verification, of course, if we could verify stuff, the first thing we would do is we would write the specification is the identity function. And then we would just, then we could solve this problem immediately, right? So this is what Andrew Appel would call the full employment theorem for quantum tools researchers, I'm sure. So the problem is hard. So there's plenty of reason to work on it. And so the way I see it is, plainly, what can we verify about quantum programs in polynomial time? That is the question. And then it's essentially abstract interpretation to the rescue the rest of the way. So abstract interpretation kind of starts with interpretation. So I want to say just a little bit about how interpretation works. So this is of course, quantum is essentially a physics field traditionally, and so they don't call it interpretation, they call it simulation. So when, they always talk about simulators. So if I say this a lot the rest of the way, that's my excuse. So here we have this circuit from before, and then one can write down that what's happening here is we're applying Hadamard, that's what this H stands for, Professor Hadamard, to this first qubit, and we're doing nothing to the second qubit. That looks like that in math. This is a tensor product. And then these two qubits we started with here, that's a tensor product of two qubits there. And the tensor product is really what causes this doubling effect every time we add a qubit. And then we can use laws of algebra to compute something, and we end up with this, which is then exactly this, this vector that I showed earlier on. And so there's sort of different ways one can calculate this and sort of make something out of it. And people have implemented lots of simulators to do this in practice. There's sort of a web page that lists at the moment 76 active simulator projects. I teach a sequence of 2 quantum classes at UCLA, and in one of those, all the students implement a simulator like this. So maybe I can just say it's not that hard. It's like a 1-week homework, so it can totally be done. And what we want to do then is to start to abstract. And so what does that mean? It means that we need to look very carefully at this, where this is what happens all the time. You have a state vector, kind of a big one, right? Sort of exponential in the number of qubits. We have a matrix. We're taking a step of computation by doing that. So this means that what we need to learn to do is to abstract the vector and then abstract the matrix, right? So that's our business. And so that's not sort of the normal thing that we just went through some talks where they abstract all kind of other data structures, but vectors are sort of a little bit unusual. And so this is kind of where we need an idea. And so one of the things one can ask is, okay, so where are the hard cases? So we're kind of used to from classical programs that loops and recursion and so on, okay, so we know that's part of the hard cases. So I just want to hammer home a point here. There's a famous theorem called the Gottesman-Nel theorem that says that there are easy cases. And the easy cases has to do with these 3 matrices here. So they're actually kind of listed down here what they are. But what the theorem says is that if all you're using are those matrices here, and you can derive a lot of other interesting matrices from them by multiplications and such, you can build a lot of interesting stuff that all can be simulated in polynomial time. And so all this stuff about exponential time that's sort of embedded in the whole story here just sort of vanishes. And one of the interesting things is that all the error correction that people are studying today, maybe not so much this new stuff that's coming up, but all the stuff that people have been experimenting with for years, is all within this gate set here. So the error correction is actually in the easy part of quantum computing. The other story is that down here in the corner is hiding this thing here called t, and that's the hard one. And the funny thing is that t squared is equal to s. So if you just notice in the bottom right corner, the square of this thing is this thing, as you can see. And that suddenly changes everything. So that matrix is the reason why quantum computing gets to be sort of an exponential time problem. And so all the algorithms that do something smart, like Shor's algorithm and physics simulation and so on, of course, they use this one. Or the equivalent. So, okay, so this means that we're not going to do this. We are going to do the thing, sort of the full thing. And so before we start to abstract matrices and vectors, let me just start with saying that we need some assertions. And so I don't want to show this. So there is something about this which let me just, so I think I copied a slide in the wrong spot here. So that was, so if I somehow need this later, then I will on the fly copy it back. So here comes an idea for writing assertions. So so there's some papers that we learn from, and what they do is that they use projections. So this is like mathematical projections, and so this goes sort of all the way back to old times where they started to build projections as a logic for quantum mechanics. So now we're back in the 1930s. And so we thought, okay, great. So these papers here, they show how you can build a Hall logic out of using projections as assertions. And the second paper shows then how you can do some runtime verification. So we thought, great, if it's good enough for them, it's good enough for us. And then we decide to focus on these kinds of assertions. And so this is plainly saying that the state of the whole quantum computer is over there, and the state can be described as being in a span of two vectors. And so here's an example down here. This thing here is in the span of these two vectors. And so one place where this is useful is that in quantum computing we have Grover's algorithm. And Grover's algorithm is sort of about searching for something in an unstructured space. And the main thing that Grover's algorithm does is that it rotates around in a two-dimensional space. So it is a very big vector that looks scary, but actually is just moving around in a two-dimensional space. And so it means that this thing here can be used to state the loop invariant of Grover's algorithm. So that's an example of a good thing. So now we have assertions, and then we need to think about what can we then do. We need to certainly abstract vectors, if nothing else. So the second sort of the observation there is to move from vectors to matrices. And so this is sort of a standard thing that the physics people do all the time. They take what I would just think of as the state vector of the program, and they do an outer product. So this notation here, that's the vector, and then this thing is the conjugate transpose of the vector. So it's a column vector, right? So you transpose the vector to a row vector, conjugate all the complex numbers, multiply it by itself. Now you get what's normally called a density matrix in physics. And so this means that before, when we would apply some matrix V to our state vector, now as it happens, you have to do this. So V, and then this density matrix, and then V conjugate transpose. And then now we can sort of compute. We just represent our data in a different way. So it turns out that computing, so thinking about these density matrices is a very good idea for thinking about how can we abstract, because now there's some ideas that present themselves. And so just to give an example of what it looks like, so here's a vector. So this vector here it's a this 0, 0, 0, cat 0, 0, 0 as it's called, has a 1 and then 7 zeros. And then when we do conjugate transpose, now instead it's a row vector with one lot of zeros. And when you do the outer product, there's a 1 sitting up there and then a lot of zeros. So that's a density matrix there. And so now comes really this question of how do we abstract that? And so here we use another idea that I think is kind of from physics as well, which is let's, instead of having this giant projection, which it is, this matrix, I just think of it as a projection because it is, let's instead abstract it out as a tuple of small projections. And the way we abstract it out is to say, well, so this projection there, this giant thing was an outer product that eventually came from 3 qubits. We don't need to look at all 3 qubits at a time. Let's just look at some of them at a time. I think that's sort of a standard idea from classical computing as well. We can look at a few variables at a time. And so here, if I call these 3 qubits 0, 1, 2, I could look at 0, 1, I could look at 0, 2, I could look at 1, 2. And the idea is that this will give me 3 4x4 matrix, 4x4 matrix, 4x4 matrix, so sort of 2 qubit matrices instead. So we would call that a local projection, where the local has to do with the qubit numbers. And this is very much related to idea that they use that in physics too, in some sense. They like to think about these things. So you can see here's my example from before. Now I have projected down to, well, they look the same because this is all very uniform. But now my abstract state is going to be a tuple of matrices that are much smaller than the matrix for the whole state space. And that is great. So of course we will see too that we get polynomial in many of these and that the size of them is not too big, and then that means we can now do polynomial computation on them. And that's that's where I will get the polynomial time and polynomial space for everything I'm going to say. So okay, so what are we going to do then? We just need to make the usual picture work. So we have a density matrix. We can take a computation step on the density matrix in the way I explained before. And then we want to do some kind of local projection to what in physics they would call a reduced density matrix, and I would just call local projections. And then we need to learn to take abstract steps on those. And so if we can do that, then we are pretty much in business. And so the abstract steps, that's then, of course, where we need to abstract the matrices. And so this means that we just need to get a Galois connection to work, and then we've got it, right? So now I will build such a Galois connection. And the point here is we're sort of already on the way to building this alpha by saying we have a big projection, and we are going to.
I have a little question. The projection breaks entanglement between states.
It does break some entanglement. So you're losing something. So,
you lose something.
It's a very, what you're asking is the very concrete thing that can be lost. Yeah. And so the question is, can we choose the abstract domain, the subset of qubits we are working on, so that we don't lose too much entanglement? We're surely going to lose some.
So you may generate false alarm from that.
We absolutely may. Absolutely. And we may end up with top, as was mentioned earlier, which I have never seen so many tops in my life as in this project here. Okay. Okay. So we are on the way to building an alpha by like chopping up a big matrix into small matrices, and then the question is, then we need some details here to actually do the abstract operation. And so here comes a story about how to make the abstract interpretation work. So I feel great. Both Muli and Reinhard Wilhelm are here. And that we're just building on their idea from POPL'29. And as it happens, Tom Reps was the shepherd when we had the paper in PLDI. So I feel like all bases are covered here. So if you just now look at how do we get a matrix like doing this, whatever this thing is doing, on qubits 1 and 2. How do we take an abstract step on that? Well, clearly, if the local projection talks about qubits 1 and 2, we can just do it. This should be fine. But what do we do if we end up looking at a local projection that talks about qubits 0 and 1? And then it looks like this one has not much to say about qubit 2. So the idea from this paper here is to say, let's find a way to bring in qubit 2. We have lots of information lying around. We have all the other local projections. They know something about qubit 2. So let's just bring that in, and then we can operate on this thing here. So that's like, it's a bigger matrix, but not that much bigger. And then when we're done with that, we can always throw away what we have lying around for qubit 2, and then we're back to 0, 1, and that's the next abstract state. And so there's a question about how do we sort of bring in this qubit 2, and so it happens in multiple steps. The first thing one can plainly do is to say, suppose this is like some reduced density matrix for 2 qubits, 1 and 2 there, for 0 and 1, and now we want to add something about number 2. Well, we can always tensor an identity matrix here. So identity matrix is like top in this world here. And then after that, we can go out and bring in information about qubit number, this missing qubit number 2, and then we can do stuff. And so this means, this is very much the story of do a little expansion, do your operation, and then forget the expansion, and then you're good. So that's how we do abstract operations. And I think the only reason I show this slide is that I implemented this abstract interpreter, and I spent all my time staring at this and then trying to get it right. And there's a lot going on, but that is the formal definition of alpha and gamma the way I understand them. And so we get a Galois connection. Everything works out nicely, and that whole story about how to execute steps is then. Everything supports the sort of the overall assertion checking theorem that says that if you run the abstract interpreter, you get an abstract state, and it satisfies the assertion, then the final concrete state will satisfy the assertion as well. So everything is good. So that, I want to sort of note that it's not given that this theorem will just kind of work. So there's its own math story to make that work separately, but it does. Okay. I just want to show that how it works with so it's very much the story the way it should be is that you apply the gamma and the abstract operation that I talked about and the alpha. It is exactly the way it should be. Okay, so here comes an example. So I promised an example. So look, here is a version of a famous program that's not the best way of programming this thing, but it does have a point to it that I will say. So this is a version of the GHC program that just does something. And so you can see that we have 3 qubits, we have 1, 2, 3, 4, 5, 6, 7, 8 matrices at play, and then at the end we can measure all of them and see what happens. And I think it's not too important what this program does, but if one starts to, so this is where I wanted to show this slide here earlier. Ha! So I just go back and find it here. So here's an execution of the program. You can see we have vectors everywhere, and so it's really sort of, these matrices over here, they transform the vector like this, and written in Dirac notation, it's like this. And at the end, you can see that the final state happens to be either the 0, 0, 0 or 1, 1, 1, and that would come out looking, well, here, I pointed the wrong place. Here's the final state, and here's how it looks in this vector notation over there. So now we scroll back to running the abstract interpreter. So it comes out like this. So we have these 3 local projections, and initially, we can sort of in Dirac notation write the initial state like this. So there are 3 4x4, 3 2-qubit matrices, and they have rank 1. So that this is sort of a thing. If you take a vector, you do the outer product with itself, you're going to get a matrix of rank 1. And so here comes another concrete way of saying what is it that we are losing. And so the rank can go up. And so, so you see there's some pluses that start to come into the picture here. So that's a sign that the rank is going up. And so we are losing this thing that that these local projections are sort of perfectly just an extract of this giant matrix that we have as the matrix for the entire state space. Because if it was perfect, the rank would be 1. But it isn't. It can be 2, as it end up being in this case. So we actually end up with 3 rank 2 matrices at the end. But that turns out to be enough, precise enough, that we can verify our assertion. Yes, I implemented this. So we had some free families of programs. So I would say that it does scale. So this was running on my laptop, or rather, it was running on the laptop before this one. We were running up to 300 qubits, and I still okay. So you can see when we get to Grover's algorithm, 300 qubits, 166,000 seconds. That's another way of saying a couple of days. And I remember going to my teenage son and saying, "Do you think this will damage my computer?" And he said, "It will destroy your computer." And sure enough, about a month later, I had to buy a new laptop. That's this one. And so I recommend using a server for these kind of projects. But other than that, we actually verify the assertions. So things are good. So 300 qubits. This is, of course, doing anyway. So everything is perfect, right? We are not modeling imperfect qubits here. So we are modeling things the way they should be. So for Grover's algorithm, we are verifying this loop invariant that I said. And for some of the other ones, we can verify more accurately what the final state is. So there is a question there of what is the right abstract domain. So I sort of just like say, let's just pick an abstract domain. So there is a column here called K, which is simply saying how many qubits are there in each set of these sets that I'm using in the abstract domain. So for these ones here, I'm using 2 qubits. So just like in the example that I gave. Once we go to Grover's algorithm, we go up to 5 qubits. And everything that starts to be a lot of stuff. And then there's the question of how big is the abstract domain in terms of how many sets are there of sort of different subsets of qubits. And so you can see it starts to be pretty big. I think there are probably better ways of doing this, of sort of smaller abstract domains, maybe better choices of sets or something. So down here we have bigger sets of qubits, but fewer of them. And so that's part of what helps things stay feasible. I think that this choice of what is the abstract domain, that's a thing for this this whole area here. And I am still wondering what the right thing to do there is. We need ideas. So okay, so this is partially a tribute to Patrick and Raja, and I think that this is something that has a future in the sense that we need better ways of abstracting the state of quantum systems. We need better ways of abstracting matrices. And I think that abstract interpretation, exactly like Huang was saying, was what first of all allowed us to even think about the problem. It allows us to communicate what we found and allowed us to stay sane along the way and actually believe in the project while I was implementing month after month and actually thinking that there was a foundation to this that ought to work. I am grateful that we could just hitch up to this whole abstract interpretation agenda and try to get something done. Thank you.
Hi Jens, nice to talk. First, if you want some accurate quantinuum numbers, I can get those to you about other times. But in the NISQ era, we're focusing on QEC experiments. It would be great. It's really hard to debug them and make sure they're correct. But they require, so Clifford plus T, but also you usually want a high fidelity enough T gate. So you're doing some kind of magic state distillation, which has a loop. And then we're also doing classical decoding and feed-forward control flow. Have you thought about how control flow and things like that can kind of fit into the story?
Yeah, so we have tried a little bit. I don't have an answer. And I think that this thing with having a loop on the side somewhere that produces T-gates is important. And now we have to think about how that even fits in. There's like the timing issue, there's the routing issue, all of this. Yeah. So we don't have a story for that, but I know that it's a problem.
Thanks.
In your penultimate slides, you gave 2 algorithms which you were doing basically two qubits per relationship.
Yeah.
And your final algorithm got 5 qubits per relationship, but a curiously low number of variable paths, basically. How did you select this?
So I think that, so first of all, the way I selected them was that I tried to make them overlap like this. And so it essentially became sort of a question of looking through the program and then seeing that the neighboring instructions, which qubits are they working on, and then almost like piecing together the control flow. Okay, it's straight line control flow, right? But making sure that sort of pieces of stretches of code can be abstracted nicely. The good news is that the main body of Grover's algorithm is not that long. So in some sense, it kind of is, but it's built out of blocks that one can understand. That I think is part of the secret.
Hi, thanks for the talk. I was wondering if you had any insights that you've observed on the factors that determine how well abstract interpretation scales with different kinds of algorithms. If I wanted to run this on Shor's algorithm, would I have to consider maybe the structure of the algorithm or the amount of entanglement? What would be that?
So I think that there's something in the question that sort of builds another, sort of opens another can of worms, which is that these algorithms here, for what it's worth, it's very easy to specify correctness or specify an assertion about correctness. As soon as we go to Shor's algorithm, so a key thing about Shor's algorithm is that it's built in phase estimation, and phase estimation is probabilistic, and so it means that the assertion is no longer an easy thing. And so to me, my answer is going to be more general than your question, but it is that we need to think harder about what are good assertions that we can work with for quantum computing. And some of that may very easily involve probabilities, or it may involve other things we haven't thought of. And so then we need to go back and look at what should our abstractions be. But for me, as soon as we get into these algorithms where the probabilistic nature really comes out in just talking about what it does, that is hard. So better assertion, we need better assertions. That's my answer.
So, in your work, I understand it as you have your density matrix, which contains too much information and nobody knows what to do with that, and you try to extract what carries really the information that drives the computations. And in some sense, your abstractions give us general structures, and then you need to parameterize. Do you get some feedback from the people that are writing the algorithm to know how to parameterize, to know how to pick your relations, and how to pick the size of the relations?
Okay, so let me say I have not met Grover, so it'll be difficult to get feedback from him, from me. The second thing is, I think that this search for which subsets of qubits to work with in the abstract domain, I think it's partially an answer to your first question. And in a way, the answer to the question from before about how do you exactly pick good sets for Grover's algorithm, I think is also partially an answer. And so there was a time where I was very optimistic about I'm just going to automatically produce the right subsets of qubits and this will work. And I never figured this out. But I think that there is a future there. That by bringing in insights based on the kind of question that you're asking, insights about how the algorithm actually works may be the way to go. And I actually think we need those insights anyway, even to specify assertions. One thing is to have an assertion about the final state, but there's a lot going on between the initial state and the final state. It would be great to have assertions, but it is difficult to know what to assert or even how to assert them. So I think we need a lot more work in this area.
So I guess it's a question about the next 40 years. So you want to analyze a quantum program, but you run your analysis on classical computer.
Yeah.
Have you had any thoughts on what you could do if you run your analysis on quantum computer, either for analyzing a quantum computation or maybe even for classical computation?
If I had a quantum computer, I think we should try this thing with verifying in this QMA sense, where we would use the quantum computer as the verifier, and then so we would make guesses whatever as fast that solver does. It doesn't really make guesses, right? But we would do something to produce instances and then of possible solutions, and we would use a quantum computer to verify them. If I had a quantum computer, that's what I would try.
So as we're taking a subset of the total number of qubits, and there are several subsets of parallelization could be possible for GPU optimization. Is there any step that might prevent that by being a bottleneck?
I don't think so. I'm simply not a good GPU programmer. I think that would be a lot of hope. I will give another example that's not this project, but a different one from Lawrence Berkeley, where they do synthesis of quantum circuits. And for a while, they were programming on like whatever machines they had lying around, and they could scale up to like 5 qubits, and that was on a good day. And then they got somebody in who was a good GPU programmer, and they scaled it last summer to 12 qubits. And so I think that something like that might be possible here, because there's a lot of inherent parallelism in the problem of saying, well, we do some abstract stuff here, we could as well do this at the same time. So I bet that a good GPU programmer could do a lot better than me in this.
Okay, last question? Okay, if not, we can take this.
Oh, it's again, where is the woman? It's once.
Here you are.
It's Kay. Okay, sorry. Hi, nice to see you again. It's an interesting journey. Actually, we've been working 5 years in a setting which is not completely research, but it's always fun to be here. This is a talk that I've worked with fantastic people. So actually, I've been working in Satora for, in these 5 years with an amazing team, a global team, basically US, Europe, and Israel. And these are the team that helped me make this talk. Shelly was actually helped me start the company, and Chandra was actually helping me here with this work, also building a WebAssembly formal verifier for Satora. John, who actually is originated many of the core IP in the abstract interpretation, and Yura is actually teaching me about DeFi. So how many of you know DeFi? No, you don't know what's DeFi 1. Okay. So DeFi is a cool buzzword. I'm going to show you a little bit. It's a buzzword for decentralized financial application. So you think about it, it's a subset of crypto, but it's kind of interesting things about crypto. Many people hate it. I will tell you a little bit about it today, and also tell you a little bit about how Satora handled it. And everything that I know here is thanks to Yura. Of course, I want to say we have a lot of people that you know from this space. Some of them are your students. Thank you. That help us here. So we are actually learning this space. We are doing a lot of things in abstract interpretation and also SMT solving, and we are interested in hiring. We are a huge group, as you can see. So what I want to talk to you about is 3 things. The first thing is DeFi and Satora. It would be basically understanding a bit what we are facing, and then I want to hint about what do we do for the static analysis. Of course, we have all the abstract domain you're familiar with, but we have a unique pointer analysis for this domain that I want to hint about what it is doing. And finally, because I'm old, I feel like it's a good idea for me to try to, and I'm probably stealing a lot of ideas from Patrick, but I want to somehow try to tell you how I want this field to progress in 40 years. I'm not going to stick around, but I want to actually try to explain how I think, and this is very subjective, of sort of how I think maybe this field can grow. Some of it has to do with the industrial experience in Satora, but some of it is just lessons which I have learned. Okay, so what is DeFi? So this is you can Google probably, you get good information, but this is DeFi in one slide. You think of a financial application that you do in the bank, but it's a financial application which is defined by code. You can define it in the language that we work in, Solidity. We also, now we're supporting Rust. It doesn't matter. It's a programming language. But the interesting thing in this programming language, you actually define, or maybe not, it's not a programming language, it's more the program. So it actually defines
how the financial computation is done. And once it's defined, it's on the blockchain, you cannot change it. Or you can change it, but it's hard to change. So these are programs that actually define financial computation. Some of them are our client, some of them are not. But for example, one example is a stable coin. So what is a stable coin? A stable coin is a coin that emulates a fiat coin. For example, a DAI is a stable coin that emulates the USD. It emulates the dollar. I don't know how many of you know, but actually DAI is actually very used. Where is it used? It's used, for example, in Argentina, because in Argentina, people are not allowed to use dollar, they use DAI. And DAI is actually, there is a sophisticated algorithm that actually implements it and makes sure that it's 1-to-1 to the dollar. And interestingly, if you look, for example, Satora actually, the tool actually found a bug in the core logic of this algorithm. So this is this algorithm is implemented in code. Oh, I don't know, this is somebody, hopefully this will stop. This, yeah, I've did a lot of mistakes, but I used to be a Windows guy, and now I switched to Apple. Oh, well, let's go down. Okay, so DAI is a stable coin. All of this Go is actually implemented here in London. It's a stable coin. USDC is a very interesting idea. You can think about it as a silly idea. The idea is every time you buy $1, this company goes and buys $1. Okay. So that's a very stable algorithm, okay? So, but funny enough, people found bugs in it too, okay? So these are stable coins. There are also exchanges. So exchanges actually have sophisticated math, nonlinear math in it. The idea is you have two coins and their multiplication is a constant. From it, you can do something even more general mathematically, which is called AMM. Some of you know from financial things there is market maker. So this is automatic market maker. So these are algorithms that automatically trade and decide your benefit. There's lending protocol. Actually, it's Aave, also the one who compounds. So these are things that you can borrow money, but there is an API in the code that you borrow money. And you can borrow this with cryptocurrency. Of course, you can maybe do it with fiat currency. And liquid staking is probably one of the most interesting things also. Also, actually, a customer of Satora is Lido. The idea is you can actually define when do you get your benefit. And it's very interesting because people, at least if you see this year, people have got a lot of rewards here. So how is it adapted? So that's an interesting domain. It's and you look at if you are bored from the lecture, you can look into DeFi Llama. DeFi Llama is a website that shows you how much it goes up and down. You need to you have a strong heart. So what happened is that you see the currency goes up and down. But the interesting thing is that even in the bear market, it's still actually holding up. Interesting, and it's actually. And you see that actually it's kind of interesting. People are buying, and now since the beginning of the year, it's starting to go up again. So but this is actually one of the most interesting things about this domain for people in abstract interpretation or formal verification. Even though these are very, very small programs, they are very, very tricky, and it's very, very hard to get them right. And what you see here, it's based on a company called Chain Analysis. Unfortunately, they haven't published the one. I wanted to have the one for 2023. It wasn't available at the time of the talk. But what you see here is kind of interesting. You see that, in fact, the number of hacks during the year, they actually get smaller. But they are getting more sophisticated. And people are stealing a lot of money. And the hackers are fantastic people, actually. They know a lot of things, maybe even abstract interpretation. And you see, these are things that, and I'm pretty sure it will be similar. You will check with Chain Analysis, but I'm pretty sure it will be similar in 2023. There were fewer hacks, but each one of them, people are pretty sophisticated. So, of course, I mean, teaching here formal verification makes no sense. So I kind of, this is, of course, Wikipedia looking at formal verification. But I actually want to give you another view of formal verification, which we didn't came, I'm sure. It came from our client. So how many of you know about Johari window? Johari window? Okay, so it seems like I'm teaching you several things. So Johari is actually coming from social science, communication science. It's actually a very nice idea. It's very, very simple conceptually. This is how you give feedback to people. If you are a manager, you have to understand this Johari. So the idea is there is what your employee knows about him and what you know about him. And you need to somehow communicate to him. What are the things that he's doing good and what are your things you're doing bad? So this is actually a client of us explaining how he views Torah, which is lovely. So what he said, this is the protocol, this is the code developer, and this is the hacker. Okay? And basically, this is the bugs that you know, and these are the bugs that other people know. And interestingly, the biggest competitor for Torah, and in fact that's what some of the things that Torah does, these are human auditors. So what are human auditors? These are white hackers. They are very, very smart. They look into your code and they find fantastic things. Okay? And actually, the Torah team has some people who are doing it actually in a good way without the tool and with the tool. Okay? So hackers usually find bugs here. They are called by these social science people. I hope I'm not. They are calling blind spots. Okay? I think Torah, and that's actually what this guy is saying, Ernesto. I don't know if you know him. This Italian guy. He's saying Torah is finding also bugs here. And why is it? Because Torah has, of course, specification, because the tool is comparing to the specification. So we are able to sometimes, it's very surprising to us, sometimes our tool finds a bug, we think it's not real. We go to the customer and the customer says, it is real, actually. And some of them, there are bugs that will allow you to completely deplete the code. So we deplete the contract. So we think that this is actually the benefit of formal verification for people, okay? That's Ernesto's idea. So why do we work in this formal verification? So in this domain, one thing which is interesting, this concept which says code is law. So the idea is all the code is open source. By the way, if you want to go to look in all these examples, they're all open. So Torah tool is not open source, but you can use a free version of it, or we can get just on the website. But the code is open source, and the code is law. Basically, if you invest in financial system like this, you actually can see the code, and the mathematical definition of it is a law. So that's very interesting. You want to verify the code. The ratio of lines of code for dollars, it's amazing. For me, because all my research is, and I work on very small programs. So this is fantastic. Like you have 50 lines of code with $10 billion. Okay, that's very interesting. Usually it's the opposite. Okay, go to Microsoft. Okay, so the interesting thing, even if the code is not small, is modular. You have this one contract invoking another contract, but you can do some kind of modular analysis to verify that. But still, even though these are small programs, they are very hard to get right. They have a lot of behaviors. They have nonlinear. They have a lot of things. And bugs are really very, very tricky to get. And I'll show you some. But if you look into all the bugs that were found this year, they are fantastic. And interestingly, if you look I remember sort of working with Patrick. He got us to the Airbus project. The code, I remember going to the Airbus system. They said we never changed the code. This is not the case here. The code is changed frequently, and new versions which are huge, and you have to do it from a business perspective. So you have to come up with a new version all the time. And it's usually not every month, but usually these protocols, at least once a year, they have to come with a new protocol, and it must be more interesting. And so that's actually make it interesting to formally verify. Here you see the maker. I mentioned these are the stable coin. Actually, you use the Sator approver, and they wrote their own spec, and the Lido team that are now launching the dual governance. It has some game theory in it. Actually, they're using formal verification. Okay, so as I said, it's an interesting domain for formal verification. And it's even interesting for Xavier, I guess. The compiler, checking the compiler is very interesting. So this is actually one of the probably favorite bugs this year. It's a protocol called Curve, which implements many, many things, including a stable coin. And it's written in Viper. Viper is a programming language like Python. It doesn't matter. But the interesting thing, you see the Viper compiler has some library to make the code safe. It's called reentrancy. It checks something about providing concurrency. But the interesting thing, the hacker was pretty smart. He understood that there is a bug in the compiler, where actually there is a bug related to how the compiler is mapping the pointers, and he exploited it. I think he stole only 10 million, okay? Nice guy. So this is an interesting domain. Actually, for us, of course, it wasn't a bad thing, because now we have them as a customer. So, and the interesting thing you see, actually, you are mapping the lock is mapped into a different location. So the hacker, which actually knows how to read the source code and the bytecode, the executable code, it knows that in fact you are not locking what you want. And then the exploiter, he actually writes a transaction, sometimes multiple transactions. And then he actually used this to exploit and take the money. So the hacks, even though this is small code, you may need sometimes several transactions, and they are executed in a rare scenario. You need to be very, very tricky to explore these things. So in this domain, and we heard from Kwong, there are a lot of tools. So of course, the tools that people usually work in this domain, and these are the most useful tool, is fuzzers. In particular, there is the called Foundry. Foundry is an open source tool which is everybody use for fuzzing. It's very, very useful. It's easy to use. People are using it. The problem with it is that it's hard to find bugs like I show you in the Curve cases, because these are bugs that involve multiple things. Of course, once you find a bug like this, it is still useful. In fact, we use Foundry when we find a bug. After we find a bug with the tool, we will show it with Foundry, because the user is actually understanding how it goes. So we use this tool after we find a bug. But it's hard to use it to prevent bugs. The other approach, of course, here need to be not to introduce a static analysis, either sound or not sound. It doesn't matter. I know here in this domain it's important for us, but I think looking from the perspective of the client, the static analysis is tricky to use because of false alarm, okay? And if you look at it in this domain, people have implemented tools like Slither and others. They implemented best effort tools, but they are actually, yes, Peter?
I mean, from my experience, static analysis is widely used. Fuzzing is very seldom used and very hard to set up. So Francesco?
Plus one what Peter is saying. I think it's false use line.
Yeah, I think
What
he said about the slide is false.
Yeah.
Okay, fantastic.
I totally disagree with the false positive issue for security, and I can take it offline with the false negative and the user in industry.
Fantastic. Actually, I recommend you. So the good thing about this domain, in this domain there are people from industry, there are people from academia. I recommend you to listen to Yannis' talk. Yannis is a fantastic guy in this domain. He's actually a static analysis. Yannis Samardakis.
Yeah, but he's not working in industry.
It's not. Let's. Can we? It's not my domain. I'm not trying to sell you static analysis so please. I'm not. So the issue is that I think what Francesco is saying is completely right. The issue is that in different domains, people use different things. Okay? In this domain where you have small code, just a second, and it carries a lot of value, people have used static analysis, and it's not useful for them a lot. And people have used fuzzing, and it is useful for them. There are other domains that I'm not talking about, so I'm not making any claim about Facebook, okay? I'm making a claim about this code. And in this code, people have, by the way, Satora is using static analysis. That's not, so we are using a lot of, okay, I want to continue, please. Thank you. Okay, so yeah, good. I might do, okay. I need to go on time. I want to go to the juice, actually. Okay. So the third thing that people use, bounded model checking or tools like Daphne and others, actually Satora is similar in many respects. It's basically use what's called deductive verification. You take the code, you reduce it to a formula. This is great, but it's computationally expensive. And of course, in this domain, people use, and if people have used successfully tools like Core, K, Lean. This is also interesting, especially because you can get some code to be right, and it's but it requires a lot of effort. And I think, at least from what we see in our client, it's very hard. So maybe that's, and I'm sorry I don't have all the tools here, but I'm just trying to explain what happened in this domain. It's very, very only for this crypto domain. So on the left hand, you see all these very, very powerful tools. And on the right-hand side, you see tools which are easy to use. And here I'm using both static analysis and fuzzers, so they're all together. They're more easy to use because they don't require specification. We are trying to build something in the middle. We are trying to build something which is maybe not as powerful as Quark. I know now I have to use another name, but I forgot. But it is actually, it's running on the executable code. We are trying to make the tool easy to use, and we are trying to make the tool without false alarm, and you can check it. We are modular, but unlike tools like Daphne or Vipers, we're not requiring pre and post condition for every procedure. We're trying to be, and actually there we have Jochen from Andreas, thank you. So we are trying to make it so we can scale it up. And there's a white paper, you can read about it. So how does it work? We basically have the technology, which is the Satora prover, which involves static analysis and abstract interpretation and SMT solving. And we also have something I'm not going to be able to talk about, but we have mutation testing to check the spec, because part of the bugs that we have are actually in the spec themselves. So we are trying to check them. And we have a language that you can define Hort triples, but you can also define relational properties. So we have a spec language, and this is open. You can use for writing the specifications. So how does it work? I mean, it's not any use for any of you. You have this invariant, you have this property that you want, you have the code, then you feed it to the Satora prover, and you get a proof, and you get a bug. And the bug is actually indicating some kind of what we call counterexample to induction. You are starting from a state that satisfies the invariant into a state that violates the invariant. Of course, it's not the truth, because the SMT solver or even the static analysis can time out when you have a complex code, and it is the case for us. It is the case for us. We have problem with the static analysis, we have problem with the SMT. So in practice, it's actually pretty much more sophisticated. Here I'm showing you the tool chain for EVM. We have something similar for WebAssembly. So we start from the solidity, we take the compiler, we take the EVM. This is interesting, actually. We decompile the code into high level. It's called TAP. It's our own internal representation where we handle many things. This we are implementing actually abstract interpretation here. So basically we have this tool, and that's what I'm going to show about trust by verify. We have abstract interpretation of low-level memory. And actually you see that one of the benefits of this tool, because it enforces stronger of invariant of the code, we are finding bugs in the compiler itself. So we are not formally verifying. The compiler is more like translation validation. We are checking properties of it using abstract interpretation. And of course, this is actually where we have a lot of IP, but I'm not going to talk about it. It's more Yaroslav's work in the SMT team here actually in Europe. Darion, we are actually doing a lot of things to make the SMT solver, of course thanks to Nicola and others, to make the SMT solver work. Where this tool is very, very useful is where you have, basically you are changing your code. You have a bug after exploit or something, or you have a new version of the code, and you want to check that the invariant are still maintained. So it actually goes into your code and you check it. So maybe this is just show you a simple example. This is a trivial bug. You see you have invariant here. And you see that the tool actually found that if you are doing, this is a very, very rare corner case, that you are transferring the money to yourself. And then, in fact, if you're transferring the money to yourself, you can earn money. And the way tool is, and actually this is a bug that can happen even in normal banks, by the way. So, and the way the tool checks it, because there is the environment, it checks the environment. Interestingly, you see when you fix the code, for example, here you make the code more functional, we cannot show you that you have no bugs, but at least we can show you that these environments are maintained. Okay, so second part of the talk. I want to talk to you about what we do in Sator. We do many things, but one of the things we do abstract interpretation. We take state-of-the-art abstract interpreter, but we actually have to do some more things. So what is the motivation? We are allowing the programmer to write the spec in a very high level language. Think of hot triple, or you think of even simple pre and post condition. But the code itself is written in very low level. In fact, we only see the bytecode. And this is the design decision we made. People say, we made a mistake. We ask the VC, they say, you should have your own programming language. But we are not that ambitious, okay? So we tackle the low-level code. And the interesting thing, the low-level code has all the nightmares that you have in the world. Non-linear and all of these things, and storage. And I know you guys, if you account for USMT, you think you want to use a rate here, good luck. So we know that a lot of things are hard here. And we have no type information, and the control and data interfere. So this is where we have to do things here. And the way we do is we cheat, but we check it. We basically have some assumption about the environment, and we enforce them. So maybe just very, very simple example. It's not a realistic one. So this is just a contract in solidity. But if you don't know solidity, I don't care. It's just think about it. You have arrays, or you have nested arrays, and you have dynamic arrays. So in fact, here Logozor should be happy. He has a solution, he will tell you. Okay? Do you think this solution will work, Logozor? It doesn't. So the answer is no way. Okay? This solution is great for these kind of programs. Okay? But let's see the program that we have. So this is the program that the compiler generates. Okay? And I know I'm not going to go, but you see here. And actually, if you think about solidity, you go in WebAssembly, it's the same. You see that everything is storage, and actually everything, there is a double in direction of the storage. So you need to do reasoning here. And proving this assertion, you cannot use the Logozor's algorithm or ours, it doesn't matter, wherever you want. You need to recover the low level code. So what do? We also do some kind of commutative diagram of the abstract interpreter. And so basically, in the case of the Logozor, this is working here, okay? What we do, we implement something that actually works on the low-level code. So here you see that we have actually written about all these bit manipulation, storage, what you read. And what we do from that, we recover something which is called middle level. And the middle level, you see, actually, it's almost like the same. It doesn't have the names, but it has the structural equivalence about the code. And then we can apply the Logozor or others. It doesn't matter. But the idea is you have to recover this. Okay? So this is the idea. Of course, you have to reason about what the compiler is doing. And the compiler is doing many things, which is common, actually. So, for example, memory allocation is not using malloc. It's using the concept called bump allocation. So basically, every time you allocate memory, you see now there's the storage, it's allocate the memory, it's read, so now you see this piece of memory is allocated. By the way, I'm simplifying things. The allocation need not be continuous, but I'm making my life easier. The compiler actually can deal with things that it's not continuous, but this is actually getting here. Now we are writing into storage, and it's actually, now it's initialized. So we remember the initialization. So essentially, we can recover how the memory is doing. And now you see there's another allocation. So it's still allocated. Oops. Okay, and then it must be initialized. So this is how it goes. In practice, it's way more complex. I won't be able to explain, but it's combined data flow and control flow. It's associate basically things like SSA, it associates the static location with things. It checks several things that, in fact, the compiler doesn't think about. For example, memory safety is something that let us prove all these assertions. So we're actually checking these things. You see here people are tweeting about it. That's nice. So people are tweeting about it, that we have a tool for automatically detecting bugs in the compiler. That's not the case, because this is not our intention. But still, you see that we are detecting bugs in the compiler, and we are actually getting acknowledged and bug bounty for finding bugs in the compiler with the static analysis. But the idea is the static analysis enforcing this environment and checking them. Okay. So now I'm the last part of the talk, but the most tricky. How am I doing in time? Okay, so now I have to sort of tell you what I think, and that's, again, very, very subjective. So how will it be in the next 40 years? I say, I don't know. So this is, of course, I think Patrick has done a good work here, and you guys, we just heard from Jens. We can connect with many, many fields. And abstract interpretation could be thought of in a concept that you can use to explain many things. So Peter in his group with separation logic, with program logic. Maybe you can think of database theory, logic, decision procedure. We work with algorithms, machine learning, cryptography. It's actually interesting programming language. With Sharon, we work in learning theory, type theory, and I'm sure I've not mentioned all of them. There are a lot of things that you can connect abstract interpretations. That's the beauty of it. And I think it's great. You can find more here, I'm sure. But this is wonderful. Wish 2 is actually very interesting, and that's a mistake I've done many times, and I've seen it also others doing. So how many of you know Vivek Sarkar? A few of you. So Vivek is actually, I have never worked with him, but he's kind of managed Eran Yav, which was my student, and he's telling me that I'm doing something completely wrong, and he's probably right. And so as a researcher, and so this is kind of trying to understand from a Vivek's perspective, I'm stealing a slide, sorry, how the world is looking in programming. So these are the expert programmers, okay? These are hackers, people who are really care about these small programs implementing some very, very tricky algorithms, okay? These are the programmers, and maybe Facebook, maybe they are, these are the end users. Where do you think Sartor is and actually my research is? Do you want to guess? Exactly. This is why we are here. It's interesting that we are making good money here, but it's a small domain. These are very, very small people. Actually, these are small, but you need to understand actually where you are, and I think there are different challenges. I think all of them are challenging. They are nothing bad, but I've seen people that are here and are claiming they're here, and that's not good, okay? I think you want to know, and even you, it's something you have to be conscious about. Which people are you helping? And I think we need to understand if maybe there are other domains. So I think this is Vivek's point. I think it's a good point. Okay. The other thing I learned probably from Patrick, but also from my own experiences, that less is more. That specialization is the key. Often I've seen people, including my students, say, I have this algorithm that solves everything. Usually it means it solves nothing. Okay? So what we need to know, we need to somehow understand what do we do and make certain assumptions about the domain. In Satora, every day we have this nonlinear equation with exponent, whatever, and then we show it to Jochen and say, no, we really implement that. So we need to understand what we are doing, and I think making some assumption about nonlinear arithmetic and bounded storage, what we did in the shape analysis, untyped languages, and I've seen it in our domain. There are people that say, oh, and I don't want to use name. They use a new programming language and say they eliminate all the logical mistakes. Good luck, okay? Whether it's OCaml or whatever, you're not going to eliminate logical mistakes with programming language. Programming languages are great, but mistakes in logic people do in all programming languages, probably in Haskell too, okay? So we need to have some kind of understanding of something of things, even untyped languages, they're not so bad. We are working in untyped language, and people are moving the program to typed language, and they're introducing more bugs, okay? So untyped languages, they have some problems, but we need to understand at the end of the day, people care about correctness, okay? And correctness doesn't mean type safety, I'm sorry, okay? It means correctness. It means it implements what it does, okay? And part of the point to say what it does. Liveness is actually something that in the beginning of my career I've ignored, but one of the things I learned in Satora that actually liveness is very interesting. When we ask our clients what they care about, they usually care about liveness. The most interesting properties about DeFi is what's called solvency. I deposit the money, I want to be able to eventually withdraw it. Okay, and most of the bugs, the interesting bugs that Satora finds, or human find, they are solvency issues. Okay? We don't even know how to specify it, but that's a separate issue. But these are things that you need to know, liveness properties. But if you are caring about CTL, LTL, it's not the issue. You need to understand what they care about in terms of the property, and you need to think about the code, what they are worried from, what is the attack vector. Also data structure, we work in the work of shape analysis, but I think we and I think Hong Song later, and the separation logic people, they have done more, but I think we need to understand what classes of data structure people care about. For example, in crypto, we have Merkle tree, we have all of these things, and we're having a hard time about it. So we have a lot of tricky data structure to reason about it, and we hope people will come with abstract interpretation to solve them. And in the area of distributed system, people are looking into consensus, but there are a lot of things which are interesting about distributed system, and maybe we can tackle them. And again, the key idea is specialization. Even working in an abstract interpretation, maybe I will say something completely politically incorrect. Abstract interpretation that takes a single program is interesting, okay? If it's an interesting program, okay? And I think this is something to, at least it's my own opinion. Another thing which is probably questionable, and take it with some grain of salt, but this is my own opinion, and I think I've kind of been almost consistent here, maybe especially in the last 10 years, is to understand that actually automatic program analysis, so sort of maybe this is how I should have answered Logos's question, but automatic program analysis is very limited. The issue is that if the user is not involved in the game, it's very, very tricky to get results. So memory safety, of course, is a good idea, but the idea is you need the program to be, especially if you're looking for logical errors, you need the programmer to tell you what it's supposed to do. And assertion is one way. We use also relay guarantee in Satora. Abstraction, we can even say, and actually maybe something that you don't think it's true, at least in our domain, people are pretty sophisticated. Our users, they understand it, you know, we can explain them a concept like a join. So we can actually have them in the loop. It's not so bad. People are trying to optimize, to automate everything. But I think like Knut mentioned, sometimes actually having people understanding things, even things like widening and narrowing, it has this appeal, and if you can explain to a programmer, they can use it. And maybe another thing that is actually in Satora is a big thing for us, and maybe you don't think it's an issue. Failure diagnosis. When our tool finds a bug, it will sometimes take us a lot of time understanding what is the bug, or even if it's a timeout or whatever, it's even harder. Understanding what is it that's making the problem hard, and maybe extracting something from the code. So I think I encourage you to think of some kind of, maybe it's related to what Xavier was saying. Maybe even something like abstraction. Have the user, have the programmer involved how the abstraction is being done. The last one, probably I think I'm sure everybody here agree, we need to have more impact of this domain. I think we are a fantastic team, but I think if I compare to other domains that we work with, and I think we can have more impact. Of course, the fact that we have industry, but I don't think only in the industry, like works like Antoine Mounet that basically have open source tools that people can use, have more industrial application, find a killer application, like I mentioned already, DeFi, but maybe privacy, maybe other domains, and maybe also doing things that other domains are doing, for example, computer network, doing some public good, doing something that people care about. And maybe also find, and I think that's actually something that other domains, for example, I'm in Israel, and Israel there's a very huge, a good, strong cryptographic community. And one of the things which is lovely there, and sometimes I come, Adi Shamir will come and say, these are the 10 open problems, okay? And then we stick on it, and nobody, so we need to have a form, and maybe this is the form, But we need to have a form that we share. And actually, one of the things which is lovely about crypto, I know many people hate crypto, people share. All our clients we got them from competitors. So it's great. People share. Sharing is actually make you work better. And I think we can share. We can share open problems together to make this field more progress. Maybe Absinthe will tell us what are the things they're struggling with, and we tell you what are the things that we are struggling with. And we find ways to share. I think this is it. I just want to close with these things. I've seen it too many times, but still I want to tell you some myths about this field. So if we look into at least competitors, even coming, they always say that formal verification is something to find proofs. But I think at least for us in Satora and many other domains, the customer really wants to, I mean, they want to, from a marketing perspective, it is the case. They have, if you look into the website, they will say it's formally verified. They don't say what, and they formally verified with Satora. And then they find a bargain. So the issue is that the biggest value of formal verification probably for software and for hardware is bugs. Of course, we saw in many things that the hardest problem is computational, but it is true probably, but for us in Satora, getting the spec right is very hard, and if you want to help us, please approach us. Writing the spec for something interesting is very, very hard, and getting the spec right, we have tools now, we're also using Core and SAT and other methods, but getting the spec right is very hard for us and for our client. Formal verification, of course, doesn't produce a bulletproof code, not because of the soundness of the tool. Our tool has certain soundness issues, but I think it's more like the spec. The biggest problem is the spec. I can show you that many times we prove specs and client prove specs and it turns to be tautology or something. So the biggest problem is the spec. But even formal verification, we don't, if you look into many of the bugs that people have found in the DeFi, some of them is price manipulation attack. And price manipulation attack, you look it up, it's very, very hard to formalize mathematically. It's the idea that you do something and there's incentive and then somebody incentivizes you to do something. So there are some things that are actually very hard to find with formal verification. So we are not producing bulletproof code, but I think, and this is something that we cannot quantify now because we have a very small domain, but we really believe that our code that's used by us is more secure. And one way that you can quantify, you see that people like to steal it more, okay? People say, this is formally verified with Satora, let's use it, because it's considered to be more safe. So it is actually, and it's a small domain, we have not been around, but we think that, and people, for example, they use bug bounties, we also now plan to use bug bounties. So basically, let the community, in this domain actually, bug bounties are huge. Look at it out, look at it. So we plan to give bug bounties so people to find bugs in customers that we work with, in order, and they can find bugs in our code, in the code of the client, of course, or even bugs in the spec, which is fine. Other thing I think I mentioned, the competitor for this is basic code review or manual editing, and some people will say it's formally verified, and then it's not need to be audited, or not to need to be tested. It's need to be tested and audited. It's improved the auditing, and we have some auditors. I don't know if you know this platform called Code Arena. So Code Arena is a platform for community audit, and these people are using our tool. That's great. So it's a lot of people, and they're writing spec, and they're using the tool in the audit. And they, of course, get reward either from the protocol or from us. The last thing is that formal verification, people say that you do it after you finish testing and all the other things. We want to have something like shift left where people write the specification first. This is my hope. Not yet achieved, but hope. Thank you very much. This is sort of the takeaway just from the talk. Bug finding is hard. We use abstract interpretation and SMT together. So we do static analysis, and they help each other. So static analysis help the SMT in the complexity, and SMT help the static analysis because we have no false alarm. We give you a program. So that's the idea. And we prove the correctness of the code starting from an arbitrary state, unlike fuzzing. Thank you. Questions?
I have a question. When you spoke about the analysis of object code, do you know the source?
So the answer is, do we know the source? So
yeah.
Yes, the answer is we know the source. but we are not using the source. We are
Okay, because there was work by Xavier Rival, and the idea is that if you know the analysis of the code, if you know how it is translated, in principle, you are able to build the analysis of the object code and check it.
I know. This was part of his PhD. Remember that I was in the loop.
But he had no success.
No. So that's it. So that's.
And let me finish. And this is because of the community, which was saying, what you do is stupid. Just take a proof compiler, and you don't need any of your techniques. So there is also a problem in what you showed is what people understand and what they are ready to accept. And unfortunately, in your first picture with abstract interpretation in the middle, if you are in the middle, it's a nice picture. But if you are outside, you understand nothing what is in the middle. And so I think education is missing in your list of wishes.
Okay, so education definitely is missing. Another thing. To answer your thing about verifying the compiler, I think it's more like a question, but it's very, very hard to verify compilers. Like I think people have, another thing I should say, modesty is very, very important for our community. And I'm suffering from that. Yeah, I suffer a lot from this. Modesty is very important for us. Verifying a compiler like Solidity, the attempt is very, very hard. The thing, and also maybe I didn't say, we are Satora. We want to do something and stay alive. And we have a small budget, and we have customers that are paying us. So we need to tell, if we tell them that they need to wait until a verified compiler, that's not an answer they want. They come to us either as audit to check their code, or they are subscription to our service and they write the spec. So we need to make sure that we cannot dictate a programming language. And in fact, even we have worked with the Solidity team, and they say all the time, you look into the website, the Ethereum, that they are producing this data for Satora, and you ask them when, they say June 2026, whatever. So, okay, so we are more pragmatic. It's not a research problem, I apologize. But I think even from a research, it's not so easy to, and I think going back to Xavier's work, which I actually seems to know, this actually, I have to be careful here, but it didn't take into account the properties of the code that we are doing. We are looking into this code, and actually we do have failures. Sometimes we run the analysis, and the customer is implementing something that, for example, violates memory safety, and this is intentional. People are using violate, and that our tool will fail, and so we are, and then we do something. We have to do something specialized.
May I ask you another question? I remember an evaluation in my team in INRIA a few years ago, and the evaluator says, can you explain why abstract interpretation is a failure? So I said that's too hard a problem, but maybe you have some ideas.
So why is, I'm not sure I understood the question. The question is,
failure understand that it's very located to few people and does not expand beyond a little circle of specialists.
No. So we see here that we have a community growing of abstract interpretation. I can tell you that, for example, in my research, we work with Jorge and with Ari Gurfinkel. We work with the Linux team, and the Linux team actually really like abstract interpretation. So we are seeing. I think we have a complex theory. I don't know about you, but I'm not you could see I'm not the best educator in the world. So getting these things take time, and we can be better. Even in Satora, if you ask people, we usually ask our programmer what they want, and we think that they want us to solve timeout or whatever. They say, give a decent documentation. We say, this we don't know. So we need to find ways to make our material more accessible. If you compare, for example, to other domains, I don't know, learning theory is a very, very interesting topic, but Valiant found a very interesting way to find it. So we need to find ways to communicate. I think there is impact of abstract interpretation. The fact that the Berkeley packet filter is doing abstract interpretation, if the join is right or not right, it doesn't matter, but people understand that abstract interpretation is useful. And we understand in Satora, when I remember when we implemented the first tool, we kind of did something like Daphne or others. We did a poor man's version. And actually, it was very useful to find a bug because the code was very simple. But what happened is that once the code gets very complex, we are running after the complex code. So in fact, we are seeing, and even our customers are seeing the value of abstract interpretation.
All right, unless we have a pressing question, I think.
I just wanted
okay.
to answer to Moody, I think.
Oh, it was just for your example on the array analysis. To be exact, the paper was on abstract domain, or better, a factor abstract domain. So that was not implementation. If you go in the final section of the paper, the implementation of MSIL, which is at the bytecode level. So we analyze unstructured code. Probably easier than the one you analyze, but that was not all the analysis.
Yeah, but the bytecode that you have is bytecode of Java or something, or C#. That's not the bytecode here.
Yeah, exactly, but never say that.
Okay, let's thank Molly again.
So,
It says
yeah, okay.
Yeah.
Sorry. Yes. Yeah, I just the screen has switched. I'm
On? Peter?
Yes. Oh, thank you. Right, so it was a bit of a surprise to get asked to give this talk, and a great honor to be chatting to all of you folks. So I went to industry just over a decade ago, and it was a surprise. I had to go for various reasons, because some of my colleagues sold a startup to Meta, is why I had to go. Now, at that time, I was an admirer of abstract interpretation from afar, right? I was a theorist. I loved this lovely theory. Now, the funny thing happened is that when I went over to industry, I found that I liked it a lot more. And I want to explain why I liked it a lot more. And this is a bit of a jokey title. It has all to do with trying to deploy program analysis to people. And me as a person trying to help make program analysis. Now, the first thing that made me like it was like it more. I already liked it as a theorist, right? So after working at Meta for a while, back then it was called Facebook, that's right, I took upon the task of building a program analyzer. Now, Infer had gone into Facebook as a program analyzer based on separation logic. There's still lots of separation logic in it, but at some point, one of the engineers, Sam Blackshear, made an abstract interpretation framework inside of Infer. And so now Infer has a whole bunch of little abstract interpreters inside of it. And my task was to make a new program analyzer, and this was much easier because of that, right? Like, it had the join, it had the widening, it had lots of little abstract domains to play with. It was much easier for the analysis designer to set this up because the primitives had been discovered, and the primitives were right. So, in a sense, it was a good piece of software engineering, abstract interpretation. They made the analysis designer's task easier. Now, although we set it up using the abstract interpretation theory, so to speak. Oh, one thing we discovered as a result of this is abstract interpretation, by you folks, wasn't thought to have been finished in 1977, right? Like, there were subsequent papers, and in particular, Cousteau and Cousteau wrote many papers updating abstract interpretation along the way. For me, this made me calmer, because it's like a living subject, and it's okay to change the primitives. And in fact, we used the ideas from one paper, Abstract Interpretation Frameworks from 1994, was the one that had the right primitives that we used to set up the abstract interpreter. But we did some bad things too, right? So we implemented operations in the abstract interpreter, but they didn't satisfy the axioms that they're supposed to satisfy, right? And so we're not going to do much math in this talk, but some of the stuff that they did. Oh, I'm going to be telling a story about what I learned at Facebook, and there's later on we'll tell a story about a bit more that I've learned after Facebook, and it's all in this paper, CACM paper, and one of the authors is here, I think, and he'll catch me if I say anything wrong about his part of the work, I'm sure. But before we get started, just to keep you all calm, we'll have 2 slides of lattices, okay? And then no more lattices. And so then, I mean, we've got a transition system, and from the transition system you can get a predicate transformer. And y'all are smart enough to use backwards analysis to work out what it means to be a transition system here at the top. And given various things, you can state what it means to be an invariant in Floyd's sense, just in the lattice terms, that it's a superset of the least fixed point. And then if you find a superset of the least fixed point which is less than something you're trying to prove, then that's sufficient to prove it, right? This is how abstract interpretation works. And the interesting thing down there at the bottom is if you find something that's not less than what you're trying to prove, that doesn't disprove it, because that just means there's possible false alarms. And then part of the badness that we ended up getting into is let's say that instead of invariants, we talk about subvariants. And so X is less than the least fixed point. And so this is under approximation now, right? So I made this gadget called incorrectness logic a few years ago, and it's basically about this. And if the least fixed point is not less than X, then X is not an invariant. This gives us a way to disprove programs, is what it does. And what's very interesting is that the under approximation theory is not exactly the dual of the over-approximation theory, because the dual of the over-approximation theory is in terms of greatest fixed points, not least fixed points. But in any case, so we ended up doing some badness there, so I just wanted to keep you all calm before we leave abstract interpretation. And so in particular, if you've got an under-approximate semantics, F under bar, and an over-approximate semantics, then you can see things like the kind of badness we were doing is we were stopping unrolling while loops after n steps and saying we're done, right? And so if you do this in over-approximation land, this is very bad, right? This is not sound, but in under-approximation land, it's sound. So this is the kind of thing in our widening operator, we were doing things like that. So we'll get into sort of why we were doing things like that, but okay. Now I want to tell the story, a bit of the story of Infer at Facebook and what we learned from it. So we joined Facebook, a little startup company, but got bought by Facebook, and then we went into Facebook, and then we were started to bump into this question of scale. So these are numbers from around 2013, 2014. There are many commits per week, right? There was 100,000 commits per week, say. So if you've got a long-running program analysis, what are you going to do with 100,000 commits? It's going to be very difficult, right? So it turns out that we had an incremental program analysis, right? And so the incremental program analysis could run just on the code changes, and it could run really fast. Infer, because it was incremental, we used the word compositional. We derived the compositionality from separation logic. Because it was incremental, no problem dealing with these 100,000 commits in terms of scale. And so it would run on the code changes in the continuous integration system, and it would report any new bugs that it found on the code changes. It wouldn't report any old bugs. And it fit with the developer workflow like this. And so the scale wasn't a problem. The incrementality was very important. Right, so it did stuff like that. And it participated in the code review process. I'm just waiting for this to go. Okay. I might have, oh, okay. And so then it would write comments on the code review system on pull requests. Facebook has, of course, they don't have they have all of their own internal stuff, but it mirrors what's external. Now, something was really shocking happened after we deployed this. The first thing we did before we deployed Data Analyzer that way, we deployed it in a batch mode. We found a bunch of bugs. We made a list of bugs, and we showed the bugs to the people. Now, before this, we did what all good abstract interpretation people or program analysis people should do. We got the analysis to the point where we thought that the false positive rate for what we were reporting, which was resource errors, was quite low. We thought maybe it was 70% true positives, maybe 75%, something like that. But we thought that it was giving good signal, and then all of a sudden, 0% fixed rate. We shipped the bugs to people. People completely ignored them. So they didn't care. This was the problem. And so I had many sleepless nights at this point. I thought, like, we've just sold this company to Facebook. We just brought this tech that I love. We've deployed the tech to the people. The people absolutely don't care. What am I going to have to do? Maybe I was facing, like, going back to academia with my tail between my legs as a complete failure at that point, right? Like, this was very, 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 very scary. Then we switched on this other mode, in the workflow mode. And in the workflow, we didn't expect this, but the numbers came back. First, we thought it was over 80%. Then we found out it was 70%. It was very high fix rate. This was for the exact same program analysis, where whatever the false positive rate was, it was the exact same false positive rate. And so why would this be? Why, like, I've heard things like, it's important to put things in the developer workflow. Nobody ever told me 70% versus 0%. Nobody said, and so I was basically shocked by this. So you see, I was treating the industry, software engineering, like a scientist does the natural world. Like, we see these things, and the engineers surprise us, and then we say, oh my God, how am I going to understand that now, right? And so this was one of these things like, oh my God, how am I going to understand this now? Why is this workflow? There's a better reason, which was very interesting. And the engineers were saying things to me like, oh, it's amazingly fast and a way better experience. The speed mattered a lot, but the most important thing was, they said, losing context. So I can explain why this one deployment mode was so much more effective than the other deployment mode. So it's got to do with the mental cost of context switch. Now, suppose you're doing a mathematical proof, right? And suppose somebody says, I think I found a bug in your paper from 10 years ago. Then you need to swap out the mental context of this proof you're doing. Go back to that proof, swap that back in, which is going to be pretty difficult. Answer them, then come back, then swap back in. That's a very expensive operation, right? When a software engineer is working, and then we say there's a bug, and they have to completely swap out of the context, it's very expensive for them. They don't want to leave their workflow. If we report in this way, we're reporting bugs when they're trying to land the code. It's absolutely in the workflow. It's really, and so how much of a difference this is, in this case, was 70 to 0, right? Like, and so the consequence of this is many of the program analyses, even dynamic at Facebook as a consequence of this experience, tried to go for this mode of deployment. So speed matters, incrementality matters, learned amazing things from the people. And so this made me think of something that I had never thought of unless I bumped up against the people in the industry. So false positive rate, we are taught that this is very important. I wonder if people who haven't heard this before can tell me things that are wrong with the concept of false positive rate. Maybe they can't. Maybe we won't run this like an undergraduate lecture or something, right? Like, I'll say it like this. I say, it's good for a measure to be measurable. In an engineering context, the false positive rate is not measurable, right? Like, something that's measurable is performance. I can measure that as it's in prod. The percentage of time that the analysis crashes, I can measure that. I can't measure the false positive rate. It needs humans in the loop, right, to make guesses about what okay, false positive rate is a great theoretical concept. It's not measurable. It's less useful in an engineering context. You need to measure things when you deploy real software, or else it's going to go wrong and you're not going to know why it goes wrong. On the other hand, fix rate is a measurable concept. I can measure the rate at which my analyzer warnings disappear as a consequence of diffs. Furthermore, fix rate speaks to do they care, right? Because if they fix it, they care. If they don't fix it, they don't care. So it's not the same as false positive rate. False positive rate is a good concept, but it has lots of limitations. Fix rate is something I can measure. It's much more useful. Yes?
Question.
Yeah.
That's not enough, no? You also need a countermeasure. So
Oh, no, it's not enough. There's more than just this.
Yeah, you need a countermeasure because you can increase the fix rate by a lot by introducing a lot of false negatives. So you need a countermeasure.
Yeah, I'm not saying that these are the only measures. You have to track bug volume, which is a partial countermeasure. But I'm not claiming I have all of the measures one would want, but we track bug volume as well as fix rate. Like if you get a very small bug volume by looking at more sure errors, then your fix rate will shoot up.
Okay, we can take it.
That's right.
But it's not enough because you also need a recall measurement.
Yes. So I know what he's talking about, and we can get into that. But it was just very interesting to me to bump into the people and to see this. Now, the fix rate is impacted by a number of things, but by the false positive rate, whatever it is, also by the speed of the analysis and when it's deployed. This was very, very interesting to me. So what Facebook liked about Infer, first of all, they liked that it scaled to millions of lines of code, not just thousands of lines of code. They liked that it was incremental, so we didn't have to have the bug list deployment. They loved that it found bugs, right? So they loved that it found lots and lots of bugs. So if we explained to the VP what's the impact of Infer, it would have been like, well, for this last 6 months, some large number of thousands of bugs were fixed, right? That was one of the things. There were other things that it did, so they liked that. What they never said, the VPs never said, was it proved the absence of bugs. They never gave that as a reason for why they were happy, even though we tried to sell that to them. We tried to explain again and again, this is what it does, isn't it interesting? Never did they pay attention to that. And because of all of this, it's because of a lot of this experience that I ended up working on incorrect under approximation, Joule and others made under approximate compositional interprocedural program analyses, which were symbolic, and those were very effective. So I never would have ended up working on the bit at the bottom, which became incorrect logic, without trying to deploy this. Other people might have, but without trying to deploy this to the people. So it was very valuable for me personally going into the company, trying to do stuff, and then the gift back is I had to change my attitudes about program analysis. Now, on to the next bit. Zoncolan at Facebook. I've never explained how important this was to me, so I will explain this now. So it works for this thing Hack, which is PHP, a typed version of PHP. And the story of Hack is very cool because an OCaml programmer who really knew types went into FB and said, "Oh my God, we need types." And he took all of the OCaml notions and he put them on top of PHP. His name is Julien Verligue, which is an amazing programmer. And then he charmed or explained to the engineering population of untyped programmers how types would be great, and he won that argument. And now it's a typed company, and it's really astonishing that that happened. So anyhow, there's lots and lots and lots of this code. So Zoncolan, which is Francesco and colleagues, made a program analysis which was going after taint errors, right? So these taint errors, I hope I remember to say something about this on the impact slide. Going after taint errors. The security team and the abstract interpretation team worked together to make this. This scales like you wouldn't believe, right?
Actually, the number is larger.
Yeah, I copied this from the paper.
There is an S under Minidocs. There was an S after. We couldn't give the real number.
Yeah.
But it's more than 100.
Yeah, and it must be over. I can say it must be, since I'm not in the company. It must be over 500 million locks now, right? Like this is real scale. And so sometimes it commented on pull requests, but the majority of the impact was what I would call batch mode. Give a bug of lists to somebody, and then it works. Let me explain something more about this. So, did I get the impact of? Oh, okay. So Facebook liked about Zoncolan is it scaled to millions of lines of code. In contrast to what I said about Infer, it had few false negatives. So it was engineered to be an over-approximate abstract interpreter. The extent to which it was exactly that, I don't know. But for instance, they didn't stop after 3 or 5 iterations for the fixed point. Boom, they went for the fixed point, right? So they tried to go all the way. So they were trying to be over-approximate. Infer landed at Facebook, was trying to be over-approximate, but pivoted to under. So that was quite interesting. So a gift to me was an appreciation of when over-approximation is really good, and I'll explain that in a second. So what it was searching for was these taint analysis errors. So I won't explain this one in detail, but this says attacker can delete a user account by puts an input on line 5 that causes a redirection to any other form on Facebook at line 20. And so the taint analysis follows these kinds of things. These kinds of bugs, like Infer was trying to find race conditions, it was trying to find null pointer exceptions, memory leaks, other things. This is trying to find these taint errors. The taint errors aren't necessarily so hard from the analyzer perspective. From the human perspective, they're very difficult. Let me explain an example why they're difficult. So Infer had a taint analyzer too, because we copied Zoncolan ideas at one point for a different programming language. We found a taint error in some Google code. There's this thing called Garrett from Google. And so we found a taint error that looked very bad. And so then our engineers looked at that taint error, the Infer engineers, and they said, is this a false positive or a true positive? 10 hours later, didn't know. So then the engineers ring up the Facebook security engineers, absolute experts on the team Francesco was working with. They spend 10 hours or so on this one taint warning. Is it a true false positive or a false positive? Don't know after 10 hours. Like, tell me about measuring false positives rates. The absolute world experts can't work it out in 20 hours for one bug. So then we contact Google. Google, is this a true positive or false positive? Googlers never answered that question. They just fixed the bug, right? So that was a very entertaining situation. So Zoncolan impact was this, which is, the impact was more since then I've heard, but In the 2 years to 2019, it found over 40% of the serious security issues, let's call them SEVs, inside Facebook, and it found thousands of such. It found more than the bug bounty program found. It found more than the internal reviews. Oh, we didn't even mention fuzzing here, right? Like, Facebook had an internal fuzzing team, right? That were working really hard to deploy fuzzing at Facebook. So they weren't mentioned. I presume they found less than any of these three things. But I remember some stats because I really like fuzzing, right? Like, okay, I'll tell the story like this. Like, when I landed at Facebook, I wanted to do what Francesco and them did, right? I wanted to do taint analysis. And I remember asking all kinds of people, does taint analysis actually work? That means, does it actually find important bugs? I went through paper after paper after paper, didn't find any important bugs reported from taint analysis in the literature. And I said, oh, I'm a bit doubtful. But then, at that time, fuzzing, finding lots of important bugs in the literature, right? Good. But then, what I learned from Zoncolan is that it works, and it works really, really well when done by the correct people. So we had an internal fuzzing team, and the internal fuzzing team was trying to deploy fuzzing at Facebook. Now, fuzzing ended up covering, at that point, I think like 3% of the code or 2% of the code of the company. The great difficulty with fuzzing is I need to set up the fuzz harness, and then I need to get the fuzzer to go. That takes an enormous amount of human time, enormous. And by the way, if you write a bad fuzzing harness, you do get false positives, right? So it's a hugely labor-intensive process. So static analysis, on the other hand, covers 95 or 98 or 100% of the code at Facebook, right? The kind of static analysis we have, the compositional begin anywhere ones, can start from anywhere in the code. Not a problem. Start it from any point and go. There's problems. Nothing's perfect. There's problems, but the deployability of static analysis is light years above the deployability of fuzzing, and this makes a difference. So fuzzing, when you can deploy it, it's good. Very hard to deploy. Oh, so what I learned, though, this was, so yeah, it meant a lot to me. I don't think I ever said something so positive about Zoncolan and Francesco's presence, but it meant a lot to me because it changed my mind about taint analysis. It showed me a case where over-approximation, even at scale, works really, really well. And it made me understand fuzzing, taint, security, all that a lot better. So, but then there's a question like, Zoncolan was over, Infer was under-approximate. I mean, modulo means modulo some assumptions, right? But they were engineered to be such, designed to be such. They both had quite a bit of impact. Infer had a very, very bad time with batch mode, right? And a great time with the incremental deployment. Zoncolan had great success with batch mode. Why would that be? I mean, oh, that's very interesting, right? And the reason is the people that it's deployed to. And so Infer targeted, in the first instance, it could target the second group, but in the first instance, it's going after developers. And so there's very many developers, right? In that company, very many thousands. And so what's the job of a developer? Let's ship features. What did they say to the program analyzer? Don't slow me down. Don't give me false positives. They're very upset. On the other hand, Zoncolan was shipped to the much smaller community of security engineers. Their job is the security of the entire code base. They have all of the context. They do want to go through a list of bugs and get rid of issues. They really care if there's false negatives. So the security engineer's job is, let's find SEVs. They're not saying, don't slow us down. They're saying, whoa, be careful. And they're saying, yes, dashboards, they do. So it's not for all. You know, nobody wants false positives. Nobody wants false negatives, right? But the people that these things were deployed to had a big impact on the deployment model and what would work for the engineers. Okay, so that was, you know, I would have known nothing of this if I hadn't tried to deploy this inside the company. So, so yeah, no false positives. Right. Okay, so that was good. So that stuff I actually learned. And this talk is supposed to be in a session about the future of abstract interpretation. I don't want to be so presumptuous as to tell people about the future. I'm in the middle right now of what happened at Facebook. What happened at Facebook was I went in, tried to do a bunch of things, finally realized some stuff that I've just told you some of it, right? And it took ages to realize that, and a lot of hard work. So I'm in the middle of that again now. So I haven't realized everything yet. I'm in the middle of it, but I thought maybe it's more fun to just tell you some of the in the middle instead of the only after the fact. So I'm just going to tell you some of the in the middle bits now. So I had worked for Facebook for 8 years, and then sometimes you need a change, right? So I decided to have a change. And so then I went to this company, Lacework, which is a cybersecurity company. And what I wanted to do, I wanted to take the same, this is the first approximation of the aim, is take the experience of static analysis at Facebook, ship that to every company in the world. That would be awesome if we could do that, right? Like, that's the beginning aim. Then that's not actually possible, because not every company has the budget and everything else that Facebook has, but that was the aim. I said, I don't want this to only be for certain expensive companies, right? I would like to ship that. And so the kind of idea we have is that there's, what Lacework has is there's many cybersecurity companies out there that are basically program analysis companies now. And what Lacework has is it has dynamic analysis on the right. So there are things called agent and agentless scanning, and I'll tell you a little bit about it. And then there's static analysis on the left. And our aim, and we're doing a bit of it, is to have them talking a lot. And so I'll just explain by example a bit of this. And so we'll start with the static. And so we only shipped some products a few weeks ago. One of the products is a Zonko-like product, but here's one of the things it does. So it finds a known bug, right? A known vulnerability. So there's this CVE, which it's an exploitable CVE. The person introduces it into their code. Our tool comments on the pull request and says, you're introducing this really bad bug. Maybe you should care about it. But the interesting thing it does is it gives two additional bits of information. One of the first things a security engineer will ask, if you say you've got a vulnerability in your code, because you've got a lot, or you've got a lot amongst your dependencies, they'll say, is it internet facing? So can somebody get at it right away? We say it's internet facing. Static can't tell that, by the way. We say it's internet facing, and may active means this vulnerability is being used in production. Doesn't mean it's being exploited, but it's being used in production. So these are two questions the engineer will ask right away. And so this is a simple thing we're doing, combining dynamic and static. So static finds the problem, dynamic gives extra context. And the extra context here is more of along the lines of, should I care and should I fix it? So internet facing means you should care a lot more than if it's not internet facing. And so the kind of program analysis that we're building is quite interesting. Here's some things that I hadn't worked out before. So we're making a static analysis for first party, so for 0 days, and for third party vulns and some other things. But it breaks into two kinds. There's the buildful analysis, which means we work with build artifacts. We can do a deep program analysis like Zonkoline. Then there's these other ones called the buildless analyses. So they need to be able to scan the code without knowing how to build the code. You might do this in the IDE. And so I hadn't encountered many of these analyses except for linters first. And so then there's a number of deployments via CI/CD. My thought going into the company was, if I want to ship the whole experience to all of the companies, then I do it via CI/CD like we did at Meta, right? Like via CI/CD system. But there's this other thing that I'll explain in a minute, which has certain advantages, which is very, very, very interesting. Now, we always talk about scale, so I'm interested in this problem. Scaling not in terms of lines of code, but in terms of numbers of repos you cover and numbers of companies you can get to. And so a situation I might bump into is, oh, here's a prospective customer, and they come to us and say, I've got 1,000 repos, and I don't have CI/CD hooked up. And then they say, come in and help us with code security. And so now, it's going to be a lot of effort to hook up these 1,000 repos. And so 5 other customers are saying the same thing. And so there's this thing, CodeSec bot. There are these bots, and they're very entertaining. What they do is they hook up to Git, right? And now there's a whole bunch of Git repos that the company has. And what they do is they look at all of the events coming out of Git, or it could be Bitbucket, but all the events coming out of Bit, which says like pull request, commit, all these things. And every time it sees one of them, it does a clone, clones it into a cloud, runs the analysis, then sends the information to the customer. The amazing thing about this is that to do that, you don't need the customer to have already set up a CI/CD system. It's almost as if you're automating all of the DevOps for them. But the downside of it is, if that's what you don't know how to build. There's too many varied ways to build the programs. You know this. You download a Git repo, build the program. It'll take you a while to learn how to build it. I can't do it automatically for all the Git repos. But if I do this, then I can scale to loads and loads and loads of code bases and loads and loads and loads of companies. And so what's very interesting about this is that the power of this kind of scaling is like let's think of why are Facebook and Google valuable companies? Well, one of the reasons is because they can acquire new users for very low cost, very easy onboarding. So low cost for the user to sign up, but also the engineering team doesn't need to expand massively every time there's a new user, right? This is when they talk about scale in tech companies, they don't mean lines of code, they mean this in terms of people or in terms of customers. And so this model is very scalable in those terms. Now, it may be that the buildless analysis finds less bugs than the buildful one does, but if I find a few injections per million lines of code, and I do this for many, 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 many companies, then maybe I'll find more bugs in aggregate for humanity than if I just did it in a deeper analysis for one company. Anyhow, so what's very interesting to me and what we're working on is what kind of program analyses fit this kind of weird buildless situation. I don't know if you share my sort of delight in seeing weird buildless things deployed in this way to many, 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 many people. I find delight in it because I know it'll get to many people, but also we've got a new balancing act in program analysis to play. So, second one I want to talk about is this thing agentless. So agentless, yeah.
How do you get feedback from the people that use your tool? So you have also channel?
We have you have stuff like that, ways to talk to the customers, and you have to gather telemetry and things like that. It's early, the channels and all of that. The product as a whole has channels like that set up, yes. Posture management is this very interesting thing. Let me see how quickly I can get through this. So what this does is a cloud system, it's evolving. At any point in time, you can take a snapshot. So that means I can take one state. Right? What these things do is they take a state and then they create a graph from the state. The graph is supposed to represent the risk, where you might come under attack. This is better done with an example. The example, this is something called an attack path. And the attack path says I can go from the internet to this thing called a Kubernetes service, which has a vulnerability on it, and then I can get to a database. And this is the crown jewels. And this represents the following idea. It says I can get from the internet to this Kubernetes service, and then, well, if I can exploit that vuln, then I can start performing reconnaissance. And I can look around and maybe find the right procedure calls and whatnot to get to the database and get the crown jewels. What's very interesting is this graph is constructed from dynamic analysis. Point one. Point two, it doesn't represent a real bug. It represents a maybe bug, right? So if you think about it, dynamic analysis together with creating the graph is being used for risk prevention, right? It's not being used for bug catching. And we have various ways to try to get rid of the bug, and one of the and so we try to establish things that are called security invariants. And so there are 3 different ways to get rid of the bug here, or get rid of the potential bug here. One might be the service has no critical OSS vulns, so you would fix this by updating the vulns, and then you can check it again and again. So there's invariants, like in program verification, but they're very, very easy to check and very, very, very intentional. And so what I would just summarize, and I'll have to skip one or two of the steps here, given the timing, is that what's happening, the way people are working with this, is step one, computer grabs a snapshot. That's called agentless workload scanning. Step two, computer creates a graph. That's an over-approximation or an abstract interpretation. That over-approximation or abstract interpretation, like we talk about going over, under, it's automatically usually. That step, computer creates graph, is mostly intended for the human. The human looks at the graph and tries to say, where are the risky bits, right? And they have ways to query it, but the humans look at the graph and try to figure out where should I put my attention to make my system more secure. Then forget that I won't have time to talk about code-aware agent. Then human chooses a path, establishes a security invariant, which establishes an over-approximation going into the future, and then the computer checks the invariant. So the interesting thing to me here is that under and over are happening, but under and over are working together in a way which for me was surprising. So they're being used for prevention, bug prevention. Dynamic is being used to help with that, not bug catching. And human is totally in the loop. Human is, the abstraction is created for the human, not for the computer here. So that was quite interesting. I think in the interest of time, there's another kind of abstraction that's going on. But I think what I just wanted to do is summarize what I'm seeing in Lacework. I haven't come to a lot of conclusions yet about this new work I'm doing, but I'm quite interested in it because it's got new challenges. First, scaling to new customers is a central challenge, right? And so not just scaling in terms of lines of code. And we use in prod, maybe I'll use some more academic words. Maybe in prod is okay. There's testing time dynamic analysis, which is what mostly people think about, especially in the scientific community, right? In prod means we're monitoring stuff as it's running, really, the real workloads. And so what I found out, and which is obvious in retrospect, is that in prod it's way easier to deploy in prod to many companies and many people than it is testing time. The reason for that is because the testing setups in all of the companies are so varied, but their in prod runtimes are similar. And so we can make somewhat automated ways to attach to in prod and get results, get dynamic analysis results. Whereas if we were to try to do it for 1,000 companies for testing time, it's very difficult. So even consider this problem, I'm not meaning to bang on about fuzzing, there's other kinds of dynamic analysis. Consider the problem of deploying dynamic analysis to 1,000 companies. It's very difficult because they don't have the same testing setup. But they have this very similar because of the cloud in-prod setups. The other thing people actually like is that in-prod is more true positive than testing time, right? Like, because you'll end up with workloads at testing time that wouldn't be real. So people like in-prod. The other thing that's very interesting to me is this build-less versus buildable static analysis. And I'm seeing, not necessarily creating, just observing what people are doing, lots of static and dynamic togetherness. So compute a snapshot, generate a graph. There's another thing called workload scanning where they take a history, a 30-day history, generate a graph which is used for anomaly detection. And so this is like putting a lock on your window. This is like the burglar alarm. Both the lock on the window and the burglar alarm are done by combination of dynamic and over-approximation. Then there's other dynamic and static that's going on. And so all of this that I'm saying, that I'm observing, so the interesting static and dynamic togetherness, plus having to nail the scale challenge, it's not just my company. There's quite a fair number of cybersecurity companies growing up where they share these or some subset of these characteristics. Okay, that's basically what I wanted to say. Going forward, I'd agree with Muli's point about when we make the analysis, thinking who we're making it for makes a huge difference. That makes a huge difference for the kind of analyses you create. I think abstract interpretation has already had a lot of impact. Inside Meta, we had at least 5 teams working on it with abstract interpretation experts embedded with those teams. It had a lot of impact in that company anyhow. maybe I'm becoming like these people who see abstraction behind every tree, right? I mean, maybe that's happened to me. It might have happened to somebody before. But I reckon that, so I care much more about the spirit of abstract interpretation than the letter. The spirit is very important, and it impacts my thinking, and it's happening, and the spirit will certainly have much more impact. Okay, thank you.
Thank you very much. Mouli?
Yes, thank you for inspiring talk. So 2 thoughts. I mean, you are obviously right about the fixed rate. We also measure it this way. But if people agree to write specification, then in fact you do have, we in Satora, once the person write the spec, they know what's a false alarm. So if people, maybe in your domain it's not realistic, but in domain that people care and they are willing to write what's right, then in fact you can, so maybe that's not in your domain because people in this domain, they don't want to say what they expect. That's what you're saying. So basically you want, that's maybe a question for you. Do you want people, you think there's no way, maybe that's an idealistic question, not, do you think there is a world where people will want to write in their code or just their code? Is that your feeling that?
Right now, there are 2 groups of people we're serving. Number 1 is the security engineers, and they need to know a lot about what's happening, and they do care about the analog of specs. And if I can get excuses to verify little bits of code, I will take that excuse, right? So there's a small community of people who care about little bits of things that have totally got to work. Then there's the security engineers, that's more. Then there's the developers. All of the developers, I don't think we should think about trying to convert them. Right? They've got to make features, so I don't think they're going to be writing specs. That's going to slow them, the majority of them. I don't think we should think about this. So the way I approach it is I want all these reasoning techniques to help everybody, right? And so, okay, over approximation for security engineers, great. Full-blown program verification for people, great. I want to meet these people where they are. Under approximation for all of the developers, great. I want to help all of them. And what I really learned this at Facebook, it's important for the experts to meet the people where they are. We can change them what they're doing a bit, but to me, not make them come to us. We have to go to them. And we don't, there's another nice slogan. We don't want people to help abstract interpretation. We want abstract interpretation to help people. Right? So that's, I think we're on the same page, but that's my answer.
So the second is more a warning to you, because I think you are saying something right, but you are saying that in prod is easier. But the problem is in prod in many domains, including us, is that you're ignoring the most important thing is mitigation. Once the bug is there, the question is how do you fix it? Even if it so basically in our domain, if you find, we have actually a lot of competitors doing actually in prod, and the problem is it's almost useless or even it's hurting, because the issue is that if I find bug in your code, yes, Google most of the code they can fix, but even Google, the safety critical code is very hard to fix. So if you find it during prod, it's unless you have an automatic way to fix it, which people are trying in different things, and including us. But the issue, you understand, it's too late. It's too late. You even prefer.
Well, imagine if I went into these in-prod analysis companies, and I said, you're trying to bolt the door, or to close the door after the horse is bolted, right? And so now I'm bringing the static, the earlier. So I agree with you, but I'm not going to then say don't do the in-prod, because it does have all the advantages that I've listed. So it's very important not to take one extra advantage and then get rid of all those ones.
No, but all I'm saying, maybe there is, I don't know, there's some rule that says that the preservation, at least in Hebrew, preservation of difficulty, that maybe you should go in the middle. Maybe you should even don't abandon the testing thing, because it's...
I'm not abandoning, listen, I want to ship testing to 1,000 companies, but I just don't know how to do it.
Yeah.
And if you figure out how to do it, that's an entirely new unicorn startup.
Please. Sorry. At some point you said, so first of all you said that
forgot the name of the tool, the thin threading one. It would run in 30 minutes.
Yeah.
On what machine? Because you had Facebook, so
well,
you know.
But still, it's 30 minutes for over 100 million lines of code in the data centers.
Yep.
Running in the data centers.
Normal Facebook servers.
Okay.
It's the same servers you run Facebook on, Instagram on.
Fair enough. And the other question is.
Francesco?
We can discuss. So this particular number is one server. We have distributed architecture. We also did it for C++ distributed to others.
Thank you. And the other question.
Thank you for the question. This is just a general comment. Think of me as someone coming from industry. What we missed so far that we are forgetting here, or actually Peter talk, said is that it's very, very, very important to scale those analyses.
Yeah,
so if you think it's extremely important to make them run on distributed environment. So if you think how Google works, how Azure works, how Facebook works, how Amazon works, they work because they are massive distributed systems. When I see static analysis, they always think about the single thread, uniprocessor, and how much memory. So if I could do my desiderata, would be make your analysis distributed. Think about distributed analysis. Sorry.
No, that was interesting. And the other question is, you said it's internet facing, and you can only know that because of dynamic analysis. Static analysis can do that.
Yeah.
Why is that?
Well, because it's internet facing, because it's been deployed to a machine which is connected to the internet. So if you just look at the repo, you don't know
okay. I get it.
So the fixed rate, the 70% fixed rate,
yeah.
that it's true you can measure it, but I'm wondering, is it all really true positives, or maybe
they could be fixing
yeah, people willing to take something that's just a false positive, but they're happier because now they don't get this red flag on your build system, on your CI system?
It might be. Remember, I gave you the story where we sent a taint analysis warning to the Googlers and they just fixed it. That might have been a false positive. Nobody knows even now. So, but that's the story of types too. With types, you're fixing loads of false positives all the time, but in aggregate, you get a gain for that. But it might be. But I can measure it. It is giving signal. Do people care? Whereas false positive rate isn't giving that signal.
Yeah.
Uh-oh.
No, I just wanted to go a bit further and say it might be even good to report some false positives sometimes because they might make the code better. Like if your static analysis is more regular and more predictable and teaches engineers to write better code, then that might be at the cost of some false positives. But overall, if the tool can understand it, then that means the code, and a human can understand the code as well.
The tool is written well enough and it can't understand some code pattern, probably your code pattern is bad.
Maybe I'm being too cynical, but the incentives, there is a way for the incentive to be misaligned.
They are not evaluating.
You report 100 bugs, the programming team say, I fixed 100 bugs, none of them are really bad, but everyone is happy.
Yeah,
I'm not saying that's what you have. But
they can completely ignore the bugs and everything is fine.
They're not paid.
They are not yet. They did not change their evaluation. They do what is best for their code. So that's
where the incentive comes is if they ignore the warning and then it crashes later, or there's a big problem later, then somebody will say, well, why did you ignore the warning? But
and the other thing is also the ethics. You have to think that those are professional programmers.
Yeah.
They really care a lot about the code quality.
Yeah.
So when you give them a message and they say something can be wrong, they really care about it because it's also the reviewer who look at the code. So this is also, I guess, goes what Peter was saying, is also who is the target. Those are professional programmers. They really care about code quality.
Okay. So I have a very naive question to ask about, so you displayed some scenarios that you get from dynamics analysis that can be used to explain the false alarms or in preventions. I was just wondering how simple they are. Are they simple enough to be understood by reviewers? Or?
Which ones were we talking about? These graphs I showed?
Yeah, these graphs.
Oh, I'm sorry. The graphs, the target of the graphs is the security engineer,
Yeah.
the security expert. And so the way the security expert works is you say to them, oh my God, we've got this system. Where are the risks? I need to control the risks. And then they say, where are the assets? Where are the databases? Where are the machines? And then they say, where are the known vulnerabilities? So then they start exploring the graph, trying to get a global picture of where all of the problems are. It's like if you have to secure your brother's house, the first thing you do is say, where are the windows, right? Oh, are there locks on the windows? So first they do reconnaissance and they think about all of that. And so the graph totally helps them with that. And so the dynamic analysis is maybe like some camera that went into the house and it found all of the windows and things like that without knowing the blueprint.
So is it a big object or is it something simple?
It's huge, but
it's huge. Yes.
It's massive, but you can take views of it.
Okay.
Right? So
you have ways to explore it and to zoom in
out. And it's
out.
abstracted. Like it may be that there's 15,000 windows, or there's 15,000 hosts of some similar characteristics, so they'll be put into one node. But the graphs can be very big, and so you end up saying things like, here's a target. Here's maybe a database. Now I want to understand things going into that database. We might look at the paths going into that database instead of having to explore the whole thing. But yeah, it's big, yeah.
Okay, thank you.
Okay.
Let's thank Peter again. So the next talk will be given by Philippa Gardner about unified compositional symbolic execution.
And we are slideshow. Yes. Okay, hello everybody. Do I have a mic? Can I have a? Is it this one? Okay. I wriggle around quite a bit, so terrible. But anyway, tell me if you can't hear me. So I'm going to talk about unified compositional symbolic execution, and in 2016, I organised a meeting at the Royal Society. And Gordon Plotkin was introducing me. And he introduced me by saying what a terrible choice it was to be organizer of a meeting at the same time as doing a talk. And my answer was yes. And I had in my head, and throughout the years, I have tended not to organize at the same time as speak. And what happened this time? Well, I've organized the biggest meeting I've ever organized, and I've done a talk at Peter's 60th meeting and Patrice's 75th meeting, because how could I say no? So thank you very much for inviting me. I wonder if it's a good idea. We will see. And my ambition was to spend a huge amount of time over Christmas nailing this, nailing what it means to do, to have all these different types of semantic triples and integrate it in all the work I'm doing. Instead, I had the weight of POPL rather than the weight of this cube. The POPL weight was bigger, And also my family, not me, got COVID. So we had an interesting Christmas. So just to say, when I say unified, I'm sorry you're going to be so disappointed. And maybe one day. So what I'd like to talk about is semi-automatic analysis tools like Viper, Verifast, Infer, that sort of thing. I have my own one, Gillian. And I am a little bit different from say, Pete. So what's happened in the past has been very much, there's those amazing people doing theoretical work, and those other amazing people doing what does it mean to get the static analysis tools into industry. And there hasn't been much join between them. And so represented by these two sources, they're kept away from each other, or keeping away from each other. And then we get to someone like Pete O'Hearn, and there are many others, where absolutely these things are beginning to come together. But at the same time, certainly in Pete's case, there are the nugget ideas in those theory papers that are as simple as possible. And there's the macho industry tool with all the bells and whistles. And the connection between them is there, but it's not explicit. And I've got the luxury that I'm an academic. So I don't have to justify myself to the industrial companies. I don't have to go huge macho engineering thing. And I can actually pause and think what I personally want a bit more. So I've had the agenda for quite a few years to try to marry the theory with the sort of work we're doing at the implementation stuff. And I've come from theory, so I've got a learning curve to get to the practice. And let's see where we go in terms of how well we've done with that. And in particular, sort of one motivation, whether it would be Pete or Byron or Daniel Kronig, is what on earth are they doing in that industry tool world? And can I begin to understand it from my place? So that's the motivation for me starting with this sort of work. And a team of us developed what's called the Gillian platform, which is a platform for developing semi-automatic analysis tools for several programming languages. The two of our examples are JavaScript and C. And partly because the characters involved and just given the way things were working, there tended to be that the ideas and the thought process was going on in the implementation work, and then we would rush to get the formalism out for the whatever paper we were doing. And so the practice was leading the theory, and that's where we were for the last few years, with some good nuggets coming out. But there was something I was less happy about in terms of, I'm a theorist. So my aim is, or our collective aim is, what does it mean to marry theory and practice in perfect harmony? And let's see where we get to with this. So my current agenda and what I will be talking about now is to pinpoint what unified compositional symbolic execution is in this theoretical place. Meanwhile, we've got that Gillian platform that is full of optimizations. It's difficult code to read. And, but the ideas for this came from here. So absolutely, the original work was from here. And now we have person sitting on the two, standing on the two horses, which is Andreas, who's around somewhere there, who is, did a Haskell implementation that streamed between the two places. And in particular, this Haskell implementation and basically pseudocode that can be, with theorems proved, are happening here. And then we've got inspired by the Gillian platform with all the optimizations. And the glue, maybe one of the legs of the rider, is Daniele, who instead of working with the Haskell implementation, was working with pseudocode and proving results in the theory. But all of this absolutely inspired from what came here, and there was huge back and forth in terms of pulling out the ideas and then writing them down in this clean place. So now I start in the theoretical place, which is the goal is the integration of OX and UX reasoning in compositional symbolic execution. And what I mean by compositional symbolic execution is I'm totally inspired by the work of all those separation logics. And in particular, when you call a function, you have a specification that's working on partial memory, and you're working with the function by itself rather than with working with some whole state and main. And then the integration of OX and UX reasoning, for now, what I mean is we've got semantic triples either in separation logic or incorrectness separation logic. I've just been told from the back to move back here. So, and in particular, so this is what we're doing. And in particular, my questions are how to isolate the part that's common to both styles of reasoning, how to function compositionality in a unified way, how to be compatible with specifications that have come from elsewhere, and how to be adaptable to different programming languages, different memory models, and different implementation choices. So here we have a symbolic state, and think of this as we're in the middle of the body of a function that we're trying to analyze. And so we've got the whole state, everything is known about, we're guessing what we think the specification is. So we've got the precondition, and we've got that symbolic state. And we are doing symbolic execution using the command C and getting an outcome that can be OK, error, or missing. It can be missing because we're in this partial memory world coming from the separation logic inspiration. So we can have things can maybe not terminate, but also for a bit that we're interested in, either from the precondition in the OX world or the bit that's, from the precondition, we end up in OK, error, or missing. We know that with the OX reasoning, you can drop information along execution paths, but you can't drop execution paths. And with the UX reasoning, the flip, you can drop execution paths, but not information along those execution paths. And we have this unified compositional engine that basically, when we're doing a function call, this is just one step out of that command C, we have the whole state, we identify which part corresponds to the precondition of the specification of the function, and we consume that part and put in what we get from the postcondition of that specification. And what we have axiomatic interface that that says gives the criteria necessary for this lot to be done in a way that is sound. So let me. Oh dear. I've never managed to do that. Do you know, POPL has lapel mics just because at some Zoom meeting I went, no, when everybody else has said, yes, we're happy in the static place. So thank you, Sasha. So here we have whole symbolic state here. And we've got this specification that's either UX or OX. And we consume the precondition, get left with the frame, put in the post condition, and we've got OX or UX soundness based on this axiomatic interface, which is this. And the axiomatic interface is basically saying the partial memory is working well, that when one has path strengthening, because as you go down symbolic execution, always the resulting path condition implies the path condition at the beginning. This consume function covers the assertion we're interested in, meaning we know how the variables are working. And we have soundness and completeness properties associated with the consume and produce functions. And then we have a soundness result, whether it be in the UX or OX way. And the point about it is that these properties are independent of the memory model, independent of the language, and implementation of the independent of the particular implementations of the consume and produce functions. So now I want to go on to this Haskell implementation, emphasizing that it's just a clean version of what's going on in the Gillian implementation, but I'm going to do it at this place, and only by example. So the challenge is to get the consume function. Produce is easier. So the consume is the important one, and produce is completely uniform with respect to OX and UX reasoning. The difference between them comes in the consume. So the assertion P consists of a pure part and a spatial part. That spatial part can be can have predicates in them, or can be just the simple core cell assertions. And we have the question of, can we find a matching theta and appropriate splitting of the symbolic heap so that these two properties hold? In the OX world, we have the implication, and in the UX world, we have the satisfaction question. And this is, let's drill down. It's actually very intertwined. In fact, we've got a matching bit and a frame inference bit, which I can explain using this example. So here we have this state, this symbolic state, and an assertion. And we want to call this function. So we need to do a matching between this and some of this state. Using this consume function. So what happens is that we start with the function call. That expression gets evaluated to that v, and the theta here is corresponding to that v, and whatever you need in terms of the variables associated with the function. So we have some knowledge about how to start which in this case is the X. And at this point, we were now working completely separate from the state. And with this knowledge, we are going to match and learn about the missing bindings that we need here. And we do this using something called a matching plan, which gives automatic reordering of the assertions to find these bindings. So this is different from what's going on in Verifast and Viper, where it's up to the user to find the ordering. And we're doing it automatically. And in particular, I was emphasizing earlier that maybe the specifications have come from outside our tool. We don't necessarily have control of what's going on with the ordering. So what's happening in this case? We start off with this knowledge X. So that ends up, because of X, we now get to the Y. So here, we don't know what Y is yet. It's going to be that V. But at the moment, we've just got some variable denoting what the value of that Y is going to be. And then because we now know this bit, because given the Y and the 21, we know the Z. So given the Y and the 21, we know the Z and can write it like this. And given that we know the Z, we now know the W. And given that we know the W, we know something about the list. So this is the matching plan. And now we do the rest of the consume, which is we have that matching. And so I think the matching plan is it's very known in the community, but is not really used much in the tools associated with separation logic. The rest of the consume involving frame inference is well known and is nothing special to what we are doing. So in particular, if I show you a particular state, then what does it mean to consume? It just means finding it. So in particular, here we start off with the information that X equals 1. Because X equals 1, we know how to link that matching plan, the first part of that matching plan, to the bit of the symbolic state we need. So here we've got it. Then, because of that, we know that Y is 2. And because of Y is 2, we then know about the Z. So this Z goes away. And now, because of the Z, we know that the Y, 2 plus 21 is 23. So we go back looking at the heap again, the symbolic heap again. Or no, in this case, the concrete heap. And get to this cell here. And so we go on. And we get to the list. And at the list place, we have to do the unfolding, as one would expect. And we unfold knowing that that W is 3. Finding the next cell and ending up with 4 going to null. We found the bit we needed. And ended up here. So this bit is not particularly novel, but the matching plan before it is really rather interesting. So in particular, I still want to drill down further. And here we've got the rules for the successful rules and the error rules associated with the consume function. And in particular, for OX and UX reasoning, most of the rules are doing the same thing. In the success case, for the pure bit, we've got something, that's the only bit where things are different. And in particular, for the pure bit, if we've got an example such as this, where we know that Z is between the 500 and the 1500, then in this case, for this precondition, we haven't got the implication here. So this is where the OX difference. And here with the UX, we've got this. This is the UX difference. But this is the only difference. So everything else is the same. Oops. So. And if we go back here, with the error rules, basically we've got the error cases, and what happens with the OX world, we end up aborting if we can't find the match and stopping. The verification has gone on. And with the UX rules, we've got a subtlety going on, which is either we just let everything those particular path expressions, those paths vanish, or we fix. Sometimes we fix by abduction when we've got the resource, when we can fix with respect to the resource. So in this case, with the OX, if we don't have we don't have the resource because we've got a clash going on, then we really end up with a error, and that error won't be fixed. In the UX way, you have to vanish. In the consumer way, you abort. The OX way, you abort. But if you have a missing possible cell, in the UX way, well, actually in both, but especially with UX by abduction, you can fix that missing error. And this rule is just saying how you fix that error. So we've understood this, except for at the level of the matching plan. So in particular, we've only grabbed at what the matching plan for Gillian is. It's good with respect to the way of thinking spatially. We can work well with cells, we can work well with the predicates, but we're restricted in terms of the expressions. And we're very lucky to have Daniele on board, who knows about matching and absolutely knows the subtleties of how to think about expressions. So we're only learning from equalities, and we only have one variable as we at each step of the matching plan, and that is that's cutting out a lot of the complexity of what's going on. And just to say, we do realise it was just where we were at the time. But the pros of this is that we're actually really improving with respect to the things like Verifast and Viper, because we've got these matching plans. And we're doing it in a way that works with both UX and OX reasoning. But we've got lots to do to understand where to be in the space of how well can we get these matching plans. And in particular, it's known in the first order world how to solve the equations with Diophantine equations. And Daniele is sort of exploring how to bring this to the separation logic world that will be expanding the known ideas from this world to the separation logic place. But that's only half the story, because that's the Q theoretical result. And then actually, what are the right choices for the various tools in terms of automatically creating matching plans? I do not know the answer. And perhaps people in the audience know the answer better than me, and then there's some choices to be made that will, and suggestions that will help us here. But this is our question without knowing the answer yet. So this is where we are. And now I'll talk about Gillian, that was always our inspiration. Because of the axiomatic interface, we are parametric with respect to the implementations of consume and produce. what we're doing next, and we haven't done the theory, but we have done the Gillian tool, is that we're parametric with respect to the memory model. And so basically the history of how Gillian has been working is that you've got a core symbolic execution engine, and it's working with respect to an intermediate representation that we happen to call GIL. And it's parametric in the sense that we can put essentially arbitrary memory models in there. So, for example, we've done JavaScript and C with their very different memory models. And we can do whole program symbolic testing using the sort of correctness guarantees that CBMC does. But then can we be compositional? Can we get the working with these function specifications in this compositional way expounded by separation logic? So basically, yes, we can, and we get the sort of guarantees as Verifast and Viper, and not only do we have the starting basic actions associated with the memory model, we need core predicates to, such as that cell assertion. And this one's very much, we have the OX switch. And that's to do with the consume pure bit. I'm a bit out of time, that's why I'm going over a bit. And then we can do the true bug finding with the UX switch. And what do we need? We need to, from the missing resource, generate fixes that give us the biabduction so that we lose that missing bit. And that was something that was buried inside work that we did in JavaScript a long time ago, to have fixes from errors. That's how to think about biabduction. And that was in the OX world. And now we're in the UX world, and it just ports over very nicely. And the sort of things we do, I like this toy laboratory. I want to do lots and lots of things such as concurrency and this and that, and I'm quite happy not being so real world. But here we've got some real world stuff going on, and just recently Sasha has done some work on Gillian Rust on unsafe code for Rust. And the sort of applications we do, for a while it's looking at data structure algorithms and teaching our course in fourth year. We also have done symbolic testing for JavaScript and C in a couple of real world libraries. We've also done full verification of AWS code, this code, some of it. And this was rather lovely because they had two implementations, one in JavaScript and one in C, and we could do both of them working with the same abstractions at some point. So that was something that we were pleased about. And in particular, lots of tools do full verification in industry now, especially those academic tools wanting some respectability and also wanting to push their ideas eventually into industry. And the thing that's really good here, and it was done by Sasha and Petter, is that we've got these high-level specifications, but we're also really working at that bytecode level and going to that real-world place where, as this list very dynamically changes, so the reasoning still makes sense. And then Sasha's Rust work is on standard library, and in particular, unsafe Rust code. So the last thing I want to do is to push a little bit to the debugging that we've done for Gillian. So basically, this AWS code is awesome. they were working with these macho file logs. And the fact that they could do anything was extraordinary. And actually, there's been quite an agenda of doing debugging led by Sasha. And here's some MSc students that turn into another MSc student who's now my PhD student, who did a big step. So basically now we've got a visual debugger with a VS Code interface. I'm not going through this. Basically, we've got the debugger integrated with the Gillian engine, and we're lifting up to the source language. And if you don't mind, I will. It would be so sad not to do this, so I'm going to do this bit. It's not working. Can't hear, though. Nat, do you have anything to say, given that you're up there sorting out the AV, or do we... Yes. He's got a very lovely demo that basically is, please come and see it afterwards if you would like. And in particular, sort of the main messages are that with this interface, we can now get to the students. We've done 2 really successful labs where they're really wanting to work with this stuff. And in particular, one of the things he does is push through into that matching. So, so we can actually look at the step and the matching and work out where things are not working. So the first thing he did as an MSc student, he did the work, and then in about a week, panic, after he'd submitted his MSc report, but hadn't gone to real world code because he wanted to go to real world code, he ended up finding the AWS bugs that we'd previously found. He found only in a week with no expertise on the Gillian stuff. And we're now on to lifting the errors from the intermediate representation back to the source place, done it for Gillian while, and are now working with Gillian C, but now with respect to CBMC, not CompCert, so that we can do the lifting. And this follows on from Sasha had an internship inside AWS, where he was hooking to this work and doing comparison between the various CBMC and his work. Here's the student lab, and this is where we want to go. His PhD project is CDAP, which is this symbolic debugger. He wants an interface between the editors and IDEs and the symbolic tools. We're currently on Gillian. Jules is going to be the external supervisor, and let me say this. So wouldn't it be wonderful if we could end up getting to Infer 2? You know, the point is it's not just about Gillian. This is a general symbolic debugger. And then where does this go? That's Nat to explore. So we've got this agenda. We are beginning to marry the theory and practice together. You can see that there's much still to do. The future agenda, will I ever make Patrice happy in terms of what should this really be? Not sure. But one thing we are doing is next week, Noam is coming to visit us in Imperial, because we are, when we saw outcome logic, we went, yeah, because we'd had ideas that were in their work, and we're exploring whether it makes sense to do things together. But I was very aware of the whole incorrectness workshop, where actually should we be in this space for that? Well, it starts off with exact core symbolic execution engine with OK, error, missing, but the missings go away with by abduction, and maybe even stop, meaning you don't do any more, you decide to stop. Sometimes in the OX world, you stop and abort. In the UX world, you prune the path. So where should one be in this space, and what sort of semantic triples work with respect to these choices? I'm not quite sure. The future is not just about the unified stuff, it's also, instead of Haskell, let's do the coq work and get it more properly integrated. Andreas has spent a lot of time in the coq world, actually with a theorem proof of world, actually on CakeML and going to hardware. So he's very interested in that stuff. And a new student, Simon, is interested. And we're also very much thinking of next generation trillion. We're parametric with respect to the memory model. Our results mean that it doesn't matter what the implementation is with respect to, as long as it satisfies those properties that I put up. But actually, we can be parametric in the language too. We don't need to go to this intermediate representation that we've chosen. We can have any interpreter as long as some properties are holding. And how should we explore this and move this to the next generation? Well, we can, because we've got this axiomatic representation. Theory to practice, this integration may be on the way. And I'd like to conclude with my favorite slide, which is this the cutest photo of POPL'24? And I'd like to thank a student there who showed me this, and he came into the room going, is this the best photo? This is Katerina Irvin's son, Matteo, and Patrice, and maybe he is the next generation of abstract interpretation. How many decades will it take?
Okay, no pressure. So, question in the room? Patrick?
In symbolic execution, there is a difficulty which is induction, and in separation logic, it's even worse because the domain is incomplete, and how do you guess it has this structure or another? So it's pre-declared, but again, it's a problem in induction. So you have the problem in symbolic execution and in. So what are you doing about that?
I don't know.
So you leave it for the next generation.
I leave it for the experts. I leave it for the experts.
Okay.
Yeah. One day.
But I would say that's the only true problem.
Oh, of course you would.
The rest is engineering.
No, I get it. I get it. I just did. Yeah.
Okay. So, thank you very much for the talk.
Okay. Coucou. So we are ready to start, and I'll give the speech to Antoine.
Oh, okay. So thank you very much for this very, very special session. So just before the short talks, you have to know that this year is Patrick Scudo's 75th birthday. So 75 years. So we wanted to do something special to honor this and this set of talks. But first, I would like Patrick to come here. Just yes, please. We have also yeah, because if it's a birthday, there is a gift. So this is a gift from the organizers of this N40AI workshop. Yes, yes, please.
It's cable, no?
So yeah, Apple stuff. So, be careful. There's a lot of small parts. But okay. So yeah, start with this one, please.
It's to eat.
To start with this one.
Ah, this one I know.
Yeah. Okay, so it's a hair tag.
Yes. Then
Yes.
I put this inside.
Yes.
And then I put that to my ears, not to
No.
in case I lose myself, I can find where I am.
Yes. Yes, yes. And you have some custom also AirTag handlers with some specific customization.
Wow, thank you.
With
I have so many,
abstract interpretation themes, so that you can choose which one you use.
I have to buy bags to put all this.
Yes, yes, you have 4.
Okay, so now I have to re-put that in, somewhere to carry. Thank you. Thank you very much.
Okay. So
Okay, so I don't know if you can see this. No, yes. That's not my eye. I don't know. Okay, so we start with some friendly talks. So we'll not be too technical, but a little of technical insight. Okay, this is my very personal point of view, or not point of view on abstract interpretation. It comes back to the 80s, of course. I mean, that's the session of the old. Okay, so in the 80s, when I was there in Pisa, Pisa was, well, in Italy, computer science started there. The old was, and it is still the oldest department in the country. Actually, they delivered the first master in 1969 or something like that. So it was pretty old for the time. And well, I was interested in computer science, so that was the only place to go to make it. And I was, well, actually, I was in love with optimization methods. Well, the faces in the end is the outcome of that adventure. That I tried to find the master thesis in that field. No way. 1 year after you finish all the exams, maybe. Too long, no? So the idea was, okay, so this doesn't work. So I went to the library. I watched the names of professors that were, I like logic and optimization. So if optimization is out, try logic. And I found Giorgio. That Giorgio Levi is professor in Pisa in those years, now he retired, and actually he gave me 2 papers. One in partial evaluation, and the other one was Couzeau and Couzeau 77. Actually, 3 papers. Couzeau 77 and Couzeau 79, because by some chance he was in, I think, in Texas in 79, and he got the booklet of POPL'. And actually, I really got in love with that. Because from my point of view, this is the best paper ever. That's my personal taste, of course. And I really went through the end of that paper. And I found very few people that really reached the end of that paper. And actually, well, That's my thesis, master thesis in Italian, application of abstract interpretation to logic programs. But in Italy, you have to say that abstract interpretation came in around the 80s, so that's 88, so that's a few years before, by Giorgio Levi and Gilberto Filet. Gilberto Filet was professor in France at that time, and he came back to Italy and got the chair in Padova. And they both were working on logic programming. And the big debate was kind of religious debate, was whether doing analysis top-down or bottom-up. Oh, you can't imagine the mess. There was kind of two religious parties that was fighting all time. So I was in the bottom-up with Giorgio, and Gilberto was in the top-down. But you won't be surprised by the hairs I had at the time where I made my master discussion. And that's me. And that's the slide. At the time, there was no such a tool. And as you can see, Couzeau 77, and definition, interpretazione astratta. That was the very first picture, and I really love that picture. And then I organized ICLP, not the main conference, but a little workshop. I was just entering the PhD. And ICLP's International Conference on Logic Programming in 1992 organized a small workshop on abstract interpretation of logic programs. And for me, I didn't even know if the Couzeau were alive. Completely. I sent them an email. They were the beginning of emails those years. And he replied me. I said, oh, God, they exist. And indeed, this is the first picture has been taken by the colleague that perfectly, you can see me, that I was watching something that I was thinking didn't exist. And then it started the idea of continuing in abstract interpretation. I met Francesco during my postdoc at the Polytechnique. That was a great time, because then I moved out of logic programming in the right time. Logic programming was dying. And I jumped out exactly when it was good to jump out. And this is an invariant of my life. Each time I cross a door, it closes behind me. The University of Arizona has a big budget hall, just to tell you. Okay, then I went back to Pisa, and in Pisa I had really, really great students. Some of them are known. You may recognize Fausto, Roberto Bagnara, and Zaffarella, but Francesca Scozzari was really, really amazing. She's one of the best students I ever had. And there was a young Francesco, because I was teaching horologic, and he was, I didn't know he was there, but he was there.
My very first class.
Very first class on horologic. Yeah. Then to Verona for 25 years. And that was my group with some time in Madrid. So that was really, really a great time. So what I like, what does it mean abstract interpretation for me? This is very personal, okay? So it's the way I learn computing. Each time I come into something that concerns computation, I try to find how to interpret it in terms of relations of abstractions. And this helps me a lot. And I can learn basically everything, from complexity to computability to whatever. And in particular, and here I borrow the sentence and the definition from a good friend of mine, I'll tell you later who is, that if we take computability, which is, well, the main theory of computation, those are the big pantheon of computability theorists, and this is made by computable functions, which are very nice and clean, and so you have compositionality, extensionality, referential transparency, and Simone Martini, a good friend of mine from the University of Bologna, had this idea of calling that the standard model, as it's done in physics for the standard model. That's the standard model. And that standard model is to computer science as movement without friction is to mechanics. Beautiful, but in reality you have friction. Indeed, double sort, ip sort, they are input-output equivalent, extensionally equivalent, but they are not equivalent in complexity. So the reality is made by complexity by intentional aspect, not extensional. So for me, abstract interpretation is the right and the most beautiful and the best and most elegant theory for dealing with the friction. Whenever you have to deal with properties of code, therefore you are entering on the way the code is written, you will deal with intentional aspect of computation. And abstract interpretation gives you the way for specifying this mathematically in a beautiful way. So these are those that I know most in the field of abstract interpretation. So it's my little pantheon, okay? And those is the big pantheon of those in computability. And what I did in the last 30 years, actually, is tries to stretch abstract interpretation to reach that pantheon. And actually, what you find in the intersection is exactly what happened when the abstraction is complete. And this is the only little things I made in 30 years. But now I'm in Arizona, okay, so I play golf, it's always sun shining. But look at what's on the desk. So thanks, Patrick and Radia, and my journey will continue over there. Thank you. Next speaker is Eric.
Thank you. Maybe?
Yes, you are probably in the other screen.
Okay.
Yeah.
Yes, perfect.
Oh, looks technical.
Okay, good afternoon. Oh,
Looks,
that's the right talk.
looks
Sorry for
technical.
that.
Looks doesn't look friendly. Not at all. It doesn't look friendly at all.
I'm an old guy. I don't know computers, you know.
Yeah.
Okay, so let me try to start. Okay, so as you understood already, I'm not going to talk about the next 40 years, but rather the last 40 years. Okay?
Exactly.
So as the organizers invited me, I went to the web page and tried to sort out what I should do for today, you know. And I saw this story about generations, so I thought, okay, which generation am I in, you know? And I thank the organizers for telling me I'm actually quite old. So I'm from 1986. Actually, that's the first time I met Patrick in this little village of the Gauls, you know, École Polytechnique, which is actually rather there with the lake and everything, south of Paris, you know, on a high plateau. It's rather cold and everything. And back then you had Patrick, who was the professor of computer science, you know, the one who had the nice course on par with mathematics, which was very recent. I think it was not the case before.
But he has an Apple.
Yes.
Already an Apple.
Yeah, already an Apple. You know the story about that? Actually, I didn't thought about telling you about that, but you know that in these days in a French public institution, you should probably get Thomson or Bull or whatever. I don't remember what you should have got by these days. But you managed to get the Mac computers, and you had to go to Élysée, I think, right? I mean, you had to go. It was complex. Yeah, it was complex. Yes, I'm ready. Yes, that's true. That's right. That's true. Yes. For sure. But you managed, and that's actually a drawing from a student of my class in 87, I think. Nice drawing. And so back then, so it was a big course, algorithmics and programming, all in Pascal, and fully worked out, you know, details, lab sessions, even the interpreter, the Pascal interpreter on the Macintosh was fully described by Patrick, so it's quite amazing. I don't know many professors who do that sort of things, you know, so it's quite amazing. And so I thought, okay, this guy is serious, and I talked with him, and I was interested by computer science, and he was kind enough to invite me at at a gathering in a Esprit project. Esprit projects were European projects back then. It was in this nice place in Nice, right? With Neil Jones, Chris Hankin, and many people, some are here actually. And then I decided to enroll the PhD program. Although, I mean, he was nice enough to accept me because I was that kind of crazy student who liked category theory and algebraic topology and that sort of things. And you know, so you didn't hold a grudge against me because of that. And then I had to complete my studies. And then, meanwhile, Patrick had actually left to École Normale Supérieure. And then I followed him over there, probably in 91 or 92, I guess. And we had some very nice and tasty meetings, you know. So it's a perk of being at École Normale Supérieure. A perk is it's a great place, very many clever people, very nice scientific interaction. But of course, it's the Latin Quarter, you know. La Truffière is a very nice restaurant. We had very good meetings. And back then, we were mostly interested in, well, most static analysis were related to compiler optimization. I was more into strictness analysis for, you know, higher order lazy programming languages and that sort of thing. Although before already there were people like François Bourdon, for instance, or also Alain Deutsch a bit later as well, who actually did things on verification of back then Pascal programs, syntax, and later on C programs and stuff, verification, right? Okay. So I could fulfill my dreams of you know, travels in nice places because I was sold, you know, by Nice these nice venues, and indeed we went to many nice places, Mont Saint Michel and London and Aarhus and many others in the early 90s. Very lively discussions on static analysis, on abstract interpretation in Europe, which was fastly growing. Maybe it's more than 30 years, so I can say something about something which pissed us off for the London meeting. You know, we love our English friends, but now I'm in London, I can say things. So they invited us over on the 14th of July. You remember that? So it's the bank holiday, you know, in France. And but then we took a sweet revenge in the evening. I mean, the dinner, the project dinner we had, while Chris Hankin was actually looking the other way, we had a series of very nice and expensive digestifs and could celebrate in a nice manner. So everything didn't go that well in all meetings and in all projects. One of these was actually the ones organized by our friends in Glasgow. We had to go to the Isle of Barra, which is in Red, which is in the Altai Bredes, northwest of Glasgow. And we had to take a very small, you know, airplane. I hate, you know, flying. It was a bit scary for me. And okay, it's a small island, 1 kilometer of diameter, something like that. We had a very interesting meeting, and then on Friday we were told that the motor aircraft was broken, so we stuck the entire weekend, you know. And the island is only known for a film which is Alexander Mackenrick's 1949 Whiskey Galore film. So we saw it like all weekend. And then we obviously, I mean, it's a film about a shipwreck where whiskey bottles were on the sand, and all the inhabitants were taking them over and drinking all day long and whatever. So that's what we ended looking at these guys, because actually I think that was Philippe Poildra. I think he brought some whiskies from Glasgow to have a tasting party on Friday, and we sort of carried on with the whiskey all weekend. So it was kind of a disaster for us, at least the younger ones probably. Okay. So other things went wrong, of course, and somehow we could probably have started, you know, the libraries for abstract interpretation earlier on, before Apron, or even before Daedalus. I'm going to talk about it. So we had this marvelous, I don't know if you remember that, this marvelous research project subsidized by the French Ministry of Research. We had a monthly payment schedule, which was exactly, you know, centime by centime, you know, and then it's never been paid for. So we never could realize this thing with Bull and Iman, with the guys from Grenoble. And also, if I remember correctly, we had this very nice NSF Esprit project, Atlantique, and it was sort of desynchronized, and it was really, unfortunately, we could have gone probably much better back in these days, in the early 90s, if they had worked out. So, of course, for me, the seminal project, and I left just before that, so I'm not like Roberto. When I leave, things happen, you know. So that was Daedalus. Actually, to call me, he didn't forget me. I moved to the French Atomic Energy Commission, and so Patrick is he has a huge capacity of work, So so we worked with Randim from Airbus to see what sort of analysis could be interesting for Airbus. It was pretty new, I mean, for them, and for us as well, actually, in many ways. And then he collected from the guys he knew who he thought would be fit for that project. So somehow they called upon me. That was nice. And that was actually, so about capacity of work, I can tell you something, probably. So of course, the project was written, and you had to write really on a rush, the last bits, And that was, if I remember correctly, that was the Easter weekend of year. Not quite remember which year, but that was an Easter weekend, right? And some of our colleagues were a bit, pissed off by the fact that we had to work all weekend, to complete the file. And that was the first, I can say it's Danish colleagues. They had the first nice weekend since the beginning of the year, and they had to work, whereas it was sunny outside and everything. So that was kind of fun, but we made it. The project was very nice, at least for me. Because there was the rise of the next generation, so Antoine, Xavier Rival, Laurent Mauborgne, so I think Laurent is talking, Jérôme Ferré, so others. So Astray, of course, you know Astray. On my side there was Fluctuate, and then there's Absinthe in that project. Also Police Space did many things in that project. So for me it was the most important one in my career in abstract computation. Right? So I just want to show you, of course I didn't put all the thesis back then, David and Jérôme, I have them on my desk, this one. But I remember Bruno Blanchet, he was a young student at TNS when I was still there, and he was taken as a witness for having other people from École Normale enroll in the computer science program, And I like very much what he did say back at that time, So he says he did mathematics, and then he went into computer science, and he concludes by, some courses are quite difficult, but very interesting. So I wonder which ones. I have no idea, Okay, so then the rest, very well-deserved prizes and stuff. And I also remember that Patrick thanked his former students and his students at that time during the ceremony, which I liked a lot. So I'd like to thank Patrick for that. It's been very nice to us. The silver medal, for instance, for CNRS. And I wanted to conclude, it's past time.
Okay, so next speaker is Laurent Mauborgne. Thank you.
So, for this small talk, I will be focusing on the lectures on abstract interpretation by Patrick Couzeau. As you can see here, you can imagine Patrick Couzeau shedding the lights of abstract interpretation over the dark seas of ignorance. So, why did I choose to focus on this one? Because I I met Patrick when I entered École Normale Supérieure, which was exactly the same year where he was appointed Director of Studies at École Normale Supérieure. So for me, that's really the first aspect I knew, and it was a really nice first contact, really. Patrick Couzeau is very accessible. He's the first teacher which I saw which considered student as equal, which is very nice, and with a great sense of humor. A few years later, I became his assistant professor. So he was kind enough to share most of these lecture slides with me. I hope you don't care, Patrick, that I use these slides now for this presentation. So this is the oldest one I could find. Unfortunately, I don't have the physical slide. At the beginning there, we have physical slides and overhead projectors. But anyway, it's not too important because they all start more or less the same way, with the very simple basics. So you are lured into very simple mathematics to start with. But in fact, it's very nice to see. I mean, it's a lecture where everything is well defined from the start. And that's really the excellent point, which I liked. And that's, in fact, part of the French School of Mathematics, POPL'24 School, which Patrick followed and which had many supporters, I would say, at ENS when you like mathematics. Patrick was very close to mathematicians, like some of them in the POPL'24 School. And I remember also, even during the lectures that were done for students, some old mathematicians coming every day, taking notes. And the reason why mathematicians also followed the lectures by Patrick Couzeau was that it didn't say basic for long. So soon enough, you would see this beautiful theory exposed in front of you with many new concepts. And well, that was amazing, really, for people who like something formal. And every time it came with nice proofs, very detailed proofs. And well, maybe as you can see here, this lecture here, something like 264 slides. That was quite common. I mean, usually for one lecture of 1 hour and a half, I would say, I think, or 2 hours, I don't remember that. But it was more than 100 slides. That's strict minimum. 300 slides was not so uncommon. And so, of course, Patrick was going a bit fast on the slides, but he always added jokes, which was great, but made him late sometime. And the worst I remember was one time we were quite late, and we had something like 50, 60 slides left. So he went to this stack of slides and just took them and put them, all of them at once, on the projectors. So I must admit that this required a bit of extra personal work to fully understand the lesson there. Well, to be fair, it must be noted also that Patrick can convey his ideas with striking images that stay for, I think you all have seen these slides, which really illustrates well the notion of soundness, like that. So I've seen them in many presentations, including some by people from Airbus or people from Absence. It's been taken all over, so it's all nice. But what I prefer really is when Patrick is a poet and he uses flowers to explain abstract interpretation. I don't know if you know about that one. So that was really an excellent way to present abstract interpretation. It was really from the start, with everything starting from induction, to build the corolla of the flower. Then you had operators, and you had nice bouquet for those most romantic. And you had different kind of abstractions, excellent. Also, concretization explains, and all the 4 different properties of color connection, and with that you understand everything. Yeah, that's absolutely excellent. Well. So lectures would not be complete without examples and application. And we all know that abstract interpretation applies to basically everything in the universe, or yeah, more or less. Yeah. Well, you've seen that again yesterday evening. At that time, early when I was assistant professor, there were applications even for rockets. So go to the universe, visit the universe. But was the turning point for me was when, as Eric described, it's a very important meeting when Randim from Airbus met us in this European project. And as usual, Patrick became a great friend of Randim. That I can say, with his jokes, and I don't know how you do that, but yeah, you became great friends. And so Randim could confide and express that he was desperately needed something that was capable of analyzing his code for his new plane. So Patrick gathered the team and proposed that, well, we just do that. It was at the time a very great leap because it was caused with thousands of floating variables and hundreds of thousands of line of code. It was a bit crazy. But it was definitely not the first application of abstract interpretation, and we managed to do something, so which was nice. And for Airbus, it was not enough. It needed to go to the industrial production. I must say that Patrick was not keen on starting himself a company, so we looked for quite some time and managed to do something with Absent, which I'm very glad of because I could then contribute again, keep contributing to Astray, and have this nice tool now, which is one of the real proof of concept that what Patrick and Radia developed and taught in these numerous lectures was really worth it and applicable. So now it's something which is we sold dozens of licenses and capable of analyzing 15 million line of code. So quite successful, and really thank you, Patrick. So, well, I would like to thank the organizers for inviting me for doing this small talk and having this opportunity to praise Patrick and thank you very much.
So the next speaker is Dominique Méry. He was Patrick's first student, I think. Second, okay. David? David Bonio?
One of the most difficult things in computer science is to get the laptop connected to the projector.
Yes, it is a problem.
So we will see if it works.
Sorry.
Next speaker, Andres Podesky. Okay, next speaker is Dave Schmidt, who came from New Mexico to here expressively for this event.
Oh, a microphone. Thank you. And I had just, yeah, my wife says I should never have one of these. I had just started my studies with Neil, and he had a reading group. And Neil said, for the past year, ever since I returned from POPL, there is one paper that gives me headaches, and we are going to study it in our discussion group. Neil says, on the even-numbered days, I read this paper and I think it's one of the most profound things I have ever encountered. And on the odd number of days, I'm convinced it's just a lot of mathematical rubbish, which is telling me things I already know. And not surprisingly, it was the paper by Patrick and Roddy on abstract interpretation. And so we did study it in the discussion group, but I was such a young fellow and I was not ready for this material. But Neil pondered that a lot, and in the end, he was convinced this was profound work, and he asked Patrick to write a paper for a book, a collection of papers on program flow analysis, which was published by Prentice Hall a couple of years later. So Neil's firmly moved into the camp of being a supporter of abstract interpretation. And so that's the first little story. But this sort of leads into the second little story, and it's about how I first met Patrick, because first impressions are so important in this world. So I was studying compiler construction from denotational semantics definitions. I didn't quite see how this had anything to do with abstract interpretation. I had so many other things to worry about. But then some years later, people were analyzing denotational semantics definitions for properties about termination and safety. And then I encountered this paper. It was an invited paper at the International Conference of Computer Languages called Higher Order Abstract Interpretation and its Application to Comportment Analysis, Generalizing Strictness, Termination, Projection, and PER Analysis. And if you go back about 25 years, these were really important topics, and they were all in one paper. I thought, this is great. And I read this, and then I understood. This is really important work. And I showed this to my student, Anindo Banerjee. I said, we have to find out more about this. This is doing everything in a common framework. This all makes sense. There was a new meeting series being organized called the Static Analysis Symposium. And so Anindo and I went to Namur, Belgium, to that meeting. I think that was about 1994 or so. And I remember that meeting so well, because when I travel overseas and I arrive the first day and I'm in Europe, I'm very sleepy. And so I always sit in the back of the lecture hall just in case I nod off. And I'm sitting back there and I can't go to sleep because there's some people just behind me and they're whispering to each other. There in the front, that's Cousseau. They're saying, if he asks you a question during your talk, you should be frightened. And I looked over, and yes, I could see someone sitting in the front. He was paying really close attention to the speakers, and sometimes he would ask a question. It was always a really good question. I said, wow, that must be Patrick Cousseau. So I was so impressed by your questions, Patrick, that one day walking to lunch, and the lunches there were wonderful. And there was only 90 minutes to have a lunch there. And we never got to the dessert course. The organizers would come in and make us go back to the lecture hall. It was so frustrating. So one day, running to lunch, I run up alongside Patrick and I said, Professor Cousseau, I'd like to introduce myself. I've read your paper on higher order abstract interpretation. I've read it through and I enjoyed it thoroughly. And I have never ever forgotten his response. The first words he ever spoke to me, he said, then you are one of 5 people in the world to do so. And I still think about that response because it has at least 3 levels of interpretation. One is, I could interpret it as a compliment because I am in some kind of select group. Or I could treat it as an extreme statement of modesty by saying, well, Roddy and I do not have as many fans as Taylor Swift, but we have some. And the third statement is perhaps it's a statement of fact, like Roberto said in his presentation, that it takes a lot of work to get through one of Patrick and Radia's papers. There's so much in there, so much to learn, and there is a lot to enjoy. So I always remembered that remark. And then shortly afterwards, of course, I met Radia and then worked with Radia on the organization of the subsequent static analysis symposium. And then I met a number of the people in this room because of those interactions at those meetings and the wonderful visits to Paris, to visit at École Normale and to go out to Polytechnique. And there, of course, as Eric was saying, there were wonderful lunches and wonderful meetings in exotic places. There's no need to say all of those. And I think by now my 10 minutes is running out, so I'll tell one last story. And this is about how Patrick has a comprehensive view of topics that sometimes goes much more beyond what the rest of us can see. And so here's the story. There was one time I was visiting at ENS, and so often, of course, a group of people would walk to lunch. And so we are leaving the building at École Normale, and we're walking up the hill towards the Sorbonne, and Patrick is looking around. It was a nice day. And he said, yes, he says, this quartier, this is a great place to be. He says, you can be born here, you can go to lycée here, and then you can get a position at ENS and work here all your life. And just as we're crossing the street by the Pantheon, when you get old, you can die here and be buried here. And I didn't realize it, but he's right. There's just everything there in one place. And so it was these kinds of insights that always meant that it was just a completely pleasant experience. And I always benefited from my visits, and I'm very grateful for the support that you and Radia gave me over the years. It really made my research a pleasure to know that there were people who really understood these topics I could go to, and they would give me insights so I could do more. So really, congratulations on your birthday. Thank you very much, Patrick. You made really my career a pleasure. Thank you so much. Thank you.
Yep. And the last speaker is Rainer Willem. And
so some people think that the talks here were alphabetically ordered. I think the organizers intended a certain climax. So, it's saying a personal history, maybe you should better say my personal history. So I was one of the early adapters of abstract interpretation because I was well prepared. Harald Ganzinger and I had tried ourselves to formalize abstract interpretation. And so we were quickly finished with constant propagation, but then we looked at the syntactic frameworks like live variables, available expressions, and got into trouble. And then we found the 77 paper by Patrick and Radia, and so we learned about the trick, namely an intermediate or intermediate trace semantics from which they abstracted these syntactic frameworks. So I've seen a lot of talks by Patrick. Often he starts with trace semantics. So in my talk here, I will follow two parallel traces, and in particular their synchronization points. In 1978, the Wilhelms moved to Saarbrücken, and shortly after, the Clouseaus moved to Metz, which, if you look at Google Maps, is just 1 hour apart. What I learned there, I learned to appreciate a capability of Patrick that I think you all don't know about, namely his capability as a bricoleur. He actually remodeled their historic apartment all himself. I was very impressed. Okay, you have seen about this project, which was very essential for us, I think for people at Patrick's chair, and also at people in Saarbrücken. Maybe I can give you an anecdote about Randim, who has been referred to several times. This anecdote was in the submission to CACM, and I had to remove it due to a politically correct referee. And the anecdote is the following. I asked Randim, well, Randim, these long names, they are speaking, right? And he said, yes, they express the expectation of the parents towards the newborn child. But he denied my assumption or my guess that his name translated into this boy will be once responsible for software quality at Airbus. So that was not the right translation. It was more like this boy will bring his grandmother the porridge to the next village. Okay, so this project was very decisive for Absinthe. At the end of the project, Randim declared that Airbus would retire their old methods and switch to the ones that Absinthe had developed. Yeah, Patrick was our first honorary doctor. So in 2001, we were thinking about whom to promote to honorary doctor. And Patrick was the first that came to our mind. And we had some more relations. He received a Humboldt Award to work at Saarbrücken, Freiburg, with Andreas and so on. And I received a Gay-Lussac Humboldt Award, which was something like the corresponding award on the French side. And I've worked at ENS and Verimac and so on. And Patrick gave talks at my Festschrift Symposium and my Goodbye Symposium. Yeah, you have seen this. Astrid was an important extension of the portfolio of Absinthe. You never told me why you came for industrialization, why you came to Absinthe. Maybe because they had shown that they could do it.
You know, there was police space.
Yeah.
And the first idea of Randim was to go to police space.
Okay.
But then it was sold to
MathWorks.
And he said, you cannot have Americans take care of us. And so I proposed maybe Absinthe, but he knew you because of the project.
Okay.
And I said, you can be confident, and he said yes, so why not?
Okay.
And we had no other solution. So
it was a great move.
It's not a choice by default because he knew you, but also the other solution didn't work.
So it was a great move and a great cooperation. Now Astrid has been extended by so many features. And maybe Xavier is not here. No, maybe because that has worked twice. Then industrialization. Maybe that is why Xavier Leroy came to offer a concert. So another point of meetings was, of course, Dagstuhl. And Dagstuhl is home to many verification communities, and one of them abstract interpretation. And there have been numerous doctoral seminars on abstract interpretation, some led by Patrick, and always with a generous time allocation to Patrick. Okay, Patrick, you all have heard, seen talks by Patrick. He loves to give clear and exhaustive, sometimes maybe you could say exhausting talks. I remember one at the Max Planck Institute where he related any imaginable semantics to every other imaginable semantics. It took him a couple of hours and a couple of 100 slides. And then what was worse was I was chair of MSoft and invited him for a tutorial. And this tutorial lasted 2.5 hours. And I must confess that I briefly fell asleep in between. And I woke up and looked at the bottom of the slide and said, oh shit, he really overdoes it. 2,000 slides, no, come on. But it was a year, fortunately. It was only the year. Yeah. Okay, the book, great book. On return of the Nicola Halbwachs Goodbye Symposium, we shared a shuttle ride from Grenoble to Lyon Airport, and Patrick told me about his draft of the book of 1,000 pages. And I said, you know, in my experience, there are books that improve the world, and there are books that are being read. And Patrick asked me whether I felt that his book would improve the world, which put me in a somewhat uncomfortable position. But fortunately, he has turned this into a quite readable and beautiful book. So what is my final wish to Patrick, that our traces will continue for a while and synchronize, so that sometime later and from the people at Absinthe, I would say they wish you all the best, and they thank you for the research results on which they base much of your work, their work, and the cooperation with you, and even providing the basis for the name of the company. Okay, thank you.
Okay. The event is over. Thanks, Patrick, and thanks to all of you that have been here. Thank you very much.